important things called one is domain and another one is codomain. For example, domain is one set, codomain is another set. This consists of elements A, B, C, D. Codomain consists of the numbers 1, 2, 3, 4, 5. Every element in the domain must be mapped to some other element in the codomain. That is the fundamental thing you have to understand in order to know the transform. So transform is basically a function that performs a mapping from domain to codomain. Now comes the next important terminology in that function. Either it can be a one-one function or onto function or many-to-one function. Different types of functions are available. So this kind of mapping, I can represent it in this term, that is function from A to B. This is the general terminology used to denote the function. So this function I can represent in the form of a ordered pair. So A is mapped to 1, hence A1. B is mapped to 2, so B2, C3 and D5. So this kind of an ordered pair, I can define this function. What is more important is no two elements in the codomain must be mapped to same element in the domain. So then it becomes a problem. So we cannot call it as a function. Another terminology that is associated with the function is called as the range. So what is basically range? Range is basically a subset of this codomain. So what are all the elements for which I have a relationship with the element in domain, that I'm calling it as the range. Range here is 1, 2, 3 and 5, which is basically a subset of 1, 2, 3, 4, 5. So this is what we have to understand. So mathematically, what is basically a transform? Transform is basically a function which performs the action of mapping. That's all. So if you extend this, instead of a number or instead of a symbol, if we extend this to a indexed variable, that we call it as the time domain. So we have set of signals in time domain that forms the domain. I'm just taking this kind of signals and then I'm passing it through a box, and then output I'm doing a mapping, which is basically a set of spectrum. Then it becomes a function. So what function does now? It takes each signal into account and then it performs the mapping. That is, it is allowing us to move from one domain to another domain, that is from time domain to frequency domain. So transform is basically a function which performs the mapping from time domain to frequency domain. So this can be another view of the transform. Now comes the next question. What is another way to define the transform? So it is basically a representing the signal. By means of this mapping, it is performing the action of representation. So how it represents? It is representing through basis function. Always keep it in mind that basis function should satisfy two important criteria. One is it has to be orthogonal and then it has to span the space. From the linear algebra perspective, two important concept is transform. We have basis function. The minimum criteria is that it has to be orthogonal and then it has to span the space. So different basis function gives rise to different transform. Let us try to understand this by means of a very simple analogy. Here we have people at one end, here we have signals at another end. This is the analogy we are going to do. We know that people belongs to different categories, at least with respect to eating habit. They have vegetarian, non-vegetarian, lacto-vegetarian, so many different categories of eating habits. So based upon the eating habit, I can classify people into either vegetarian, non-vegetarian, lacto-vegetarian. Similarly, signals belong to different categories, that is stationary, non-stationary, cyclostationary. So I have a one-to-one analogy between people and signal. What we know now is the representatives of the people, whether we want it or not, it is basically MLAs and MPs. Similarly, the representative of the signal is basically basis function. So what is the minimum condition for the MLAs and MPs? Definitely they should have completed the age of 18. That means some minimum criteria is there for the representative. Similarly, what is the minimum criteria for the basis function? Definitely it has to be orthogonal and then it has to span the space. So these two are the criteria for basis function. Group of MLAs and MP, they form the political parties. Similarly, group of basis function, they form transform. What we want to conclude here is different basis function gives rise to different transforms. What are the desirable property of this transform? We have so many types of transform, starting from Laplace transform, Z transform, Fourier transform, so many types of wavelet transform, short-term Fourier transform, so many transforms are there. So what are all the properties of a good transform? So first property is basically generality. That means the transform should be in a position to represent wide classes of signals. Second one is the transform should have the ability to compact energy into few coefficient. That means once you transform a signal into another domain, all the energy should be packed to few coefficient. Then we call it as the energy compaction. Then the third one is this transform should be able to adapt it for different application. For example, the transform can be applied for enhancement. The transform can be applied for compression. It can be used for fusion. Like that, different applications are there. This transform should be able to adapt itself to different application. Then only it will be a popular transform. Last but not the least, that is computationally efficient. Transform should be computationally efficient. If it is not efficient, even if it happens to be a very good transform, it will lose its charm. The best example is basically KL transform. KL transform, it is an optimal transform with respect to energy compaction, but rarely used because it is computationally more intense. So if you want the transform to become popular, very important criteria is that it has to be computationally efficient. Then what is the need for the transform? So let us try to understand it by means of a very simple diagram. Here we have a prism, white light falling on the prism, we are able to get the VIBGR. This idea we call it as the dispersion. If a person is standing here, he will be seeing the light as a white light. If a person is standing here, he will be seeing the white light as a combination of 7 colors. So prism is the tool which helps us to explore much about the white signal. Similarly, transform is a tool which allows us to get more information about the signal. So transform is a tool similar to that of a prism which helps us to explore the signal. Now, what are all the applications? Different applications for the transform. One, with respect to biomedical signal processing, it helps us to get the important features. So feature extraction. Second one, I can apply it for denoising, and then we can go for compression. So using this transform, we can do different kinds of activity. I have listed only these three. So we will be concentrating on these three in this lecture. Now, what are the different types of transforms? So we can see that with respect to signal, we have continuous time signal and then we have discrete time signal. With respect to system also, there are two categories. So if we are dealing with continuous time signal, you can go for continuous time Fourier transform. If your signal is discrete, you can go for discrete Fourier transform. For system study, people are commonly employing Laplace for CT and then Z transform for discrete time system. So whenever you go for a transform, two important things are there. One we call it as the forward transform and another one is called as the inverse transform. Forward transform is always called as analysis, whereas inverse transform is always called as synthesis. So we can classify the transform based upon different criteria. One is with respect to nature of basis function. Next one is with respect to type of representation, whether it is a frequency or time scale. So with respect to basis function, there are two types, whether my basis function is depending upon the statistics of the input data or whether the basis function is independent of the statistics of the input data. So if my basis function is independent of the statistics of the input data, then it is almost like a prepaid mobile. I hope there are two types of mobile every one of you know. One is a prepaid, the other one is postpaid. Am I right? So most of them might be aware of these two. Either I can go for a prepaid SIM or I can go for a postpaid SIM. So your Fourier transform, your DCT, wavelet, all comes under the category of fixed one, that is prepaid. That means postpaid, we have based upon our usage, we can pay the bill. So that is the postpaid. So my basis function depends on the characteristics of the input signal. Here it is independent of the characteristics of the input signal. So how much I use, I have to pay. Here, whatever is the plan, I'm supposed to use that plan. So that is the difference between prepaid mobile and postpaid mobile. Your prepaid mobile is similar to that of statistically independent. Postpaid is similar to that of a statistically dependent one. So statistically dependent one, the most powerful one is empirical mode decomposition. Then we have singular mode decomposition. Then you have principal component analysis. Then you have variational mode decomposition. So many decompositions are available for statistically dependent transformation. Then we have frequency representation. Transform which helps us to get only the frequency information is a classic Fourier transform. If you want both time as well as frequency, you have to go for either short-time Fourier transform, Wigner-Willi distribution, wavelet transform, and its variants like wavelet packet, contourlet, so many multi-wavelet, so many different categories of wavelet transform exist. Now we will start with the discussion with respect to Fourier transform. It was given by John Baptist Joseph Fourier. It was given in the year 1809. Roughly around 200 years back, he has given this idea. That means any periodic signal can be represented in terms of simple sine and cosine waveform. That is the fundamental idea behind Fourier series. So initially his idea was rejected, and later on it was accepted because of an important personality called Dirichlet. So Dirichlet played a very, very important role. I'm sure all of you might be knowing about Dirichlet condition. After applying Dirichlet condition, people came to realize that Fourier transform can be really applied for signal representation. So what we have to understand is Fourier is a very, very powerful because he was lucky enough to get the learning from three important people. One, we call it as Laplace. So Laplace happened to be the teacher of Fourier, then Lagrange, and then Monk. These three, Fourier was very much lucky enough to get the learning from these three legends. We know very well Laplace. So Laplace is known for Laplace transform. He is considered as Newton of France. Earlier, he was considered as Newton of France. He developed the Laplace transform. Still now, it is widely used in control system and other sorts of system analysis. And everyone should be knowing about Lagrange. Lagrange is known for his contribution in the calculus. So we have different types of calculus like differential calculus, integral calculus, and nowadays people are widely using for fractional calculus. So for all these things, the initial contribution was from Lagrange. Then Lagrangian mechanics. So like there are two types of mechanics. One we call it as a Newtonian mechanics. The other one is Lagrangian. So Lagrange also had a lot of contribution in the field of mechanics. Then we have Monk. He is very much known for discrete geometry and a father of differential geometry. You see here now, Fourier happened to learn all these concepts from his teachers, and he was able to develop a very good transform. So you know very well that Fourier happened to be the son of a tailor. He was not from a big background. So his background was not so rich. He was from an average family. He was most probably the first son of the second wife of his father. And later on, he became the scientific advisor to Napoleon. Just to imagine a giant leap in his career. So all these things because of his hard work and restless, he learned a lot of concepts from these legends. If you observe Fourier transform, it will have very close resemblance with respect to Laplace transform. So teachers also play a very, very vital role in shaping the student. Then Fourier transform, we can classify into different categories like CTFT, DTFT, DFT, and then FFT. I hope all of you will be very clear in this. So let us give a relationship between different transform through this simple slide. I may not be spending much time, but still an overview is required. If we have a continuous time signal x of t, if I take Fourier transform of x of t, I'll be able to get x of omega, which becomes the continuous time Fourier transform. So what is happening here is we are moving from time domain to frequency domain. This is the idea, and this is the expression. So integral minus infinity to infinity x of t into e power minus j omega t dt. So if you ask a mathematician, then he definitely will say that we are taking the inner product of the given function with respect to the basis. So this expression, it is equal to taking the inner product of the given function with respect to the basis function. Indirectly, what we can observe is finding the frequency omega in the signal x of t from minus infinity to plus infinity in the interval dt through the basis function e power minus j omega t. So e power minus j omega t is a complex exponential that is the basis function of Fourier transform. Now you see the close resemblance of this transform with respect to Laplace transform. So what is Laplace transform? Again the same thing, integral minus infinity to infinity x of t. Instead of e power minus j omega t, we have e power minus s into t. So omega will not be there. I'm sorry, there is a simple mistake here, e power minus st dt. Now you see that there is a change in the basis function. So if you replace S by j omega, you are moving from Laplace transform to Z transform. So how this occurs? Now you see that this is your S plane where sigma is the real axis, j omega is the imaginary axis. So if you compute your Laplace transform only on the imaginary axis, that is, if you put sigma equal to 0, you will be able to get this j omega axis, so that you will be able to get the Fourier transform. So there is some resemblance between your CTFT and Laplace transform. Now comes the next thing. If you sample this signal x of t, you will be able to get the discrete time signal. And then if you take Fourier transform, it is called a discrete time Fourier transform. What is more important is you are moving from a continuous time to discrete time. You are going to sample the signal, means you are taking specific instant of time, so that you are replacing t by n into t. So if you take Fourier transform of continuous time, it is CTFT. If you take Fourier transform of discrete time signal, then it becomes DTFT. Even though my signal is sampled, my spectrum is continuous. That is the important drawback of discrete time Fourier transform. This is the expression for discrete time Fourier. Since we have sampled the signal, this integral is turning out to be a summation. Your x of n is the signal e power minus j omega n. Again, it is a complex exponential. What we have to understand is, even though the signal is discrete, this frequency is continuous. So frequency, if something is continuous, we cannot implement it by means of a computer. Naturally, we have to discretize it. So now you see the close resemblance between your DTFT and Z transform. So what is Z transform? Instead of x of e power j omega, you have x of z, x of n into z power minus n. So if you replace z by e power j omega by taking a unit circle, what you will be able to get is DTFT. That means evaluating Z transform on a unit circle, you will be able to get DTFT. So DTFT is basically evaluation of Z transform on a unit circle. So here the most important drawback is your omega is continuous. So if you discretize omega, you will be able to get DFT. So this is the expression for DFT, and computationally efficient form of DFT is basically fast Fourier transform. So almost there is a lot of similarity between one transform to the other transform. Now, whenever we take Fourier transform, we will be able to get two important information. One, we call it as the magnitude representation or the magnitude information. The other one is the phase information. Why we are supposed to get two information? Can anyone just give an idea here? If we take Fourier transform, we are able to get both magnitude and phase. Now, I'm putting a very simple question. Anyone can answer. If you know the answer, feel free to share it with us so that we will get more insight. So why we are able to get two information whenever we go for Fourier transform? Any idea? The participants can unmute their mute by, and then they can discuss the idea. It is an open discussion. No answer from anyone? Feel free, because it's not a conventional classroom. It is some kind of a discussion. So what we have to understand is Fourier transform. Whenever you take Fourier transform, the output is a complex number. Whenever you have a complex number, you have magnitude. For example, a plus jb is my complex number. Then the magnitude is square root of a square plus b square, and the phase is tan inverse of b by a. So what is more important is, whenever your transform happens to be complex, you will be able to get two information. One is the magnitude information, the other one is the phase information. If your transform is not complex, that means your output is not complex, then you will not be able to get the phase information. This is what you have to understand. This is the fundamental. Now, what is the importance of phase? That we can illustrate it by means of a very simple study. So what we are doing it here is, we are taking two images. We are taking Fourier transform of these two images. We are able to get magnitude and phase of first image, magnitude and phase of second image. That means I'm getting four information: magnitude, phase of first image, magnitude, phase of second image. As a simple study, what we have did is, we have retained the magnitude and then we have combined the phase. See what happens here. The magnitude is retained as such. The phase of the first one is given to the magnitude of the first one. The phase of the second image is given to the magnitude of the first image. This we call it as phase interchange. If you do phase interchange, after that, if you do inverse transform, what is the result? So now you can see that there are two images A and B. So this image A is basically a cameraman image. This B is basically a Lena image. So if you do phase interchange, you can see drastically that cameraman image turns out to be a Lena image, and Lena image turns out to be a cameraman image. That is the importance of phase. So what we want to convey here is, if you mix the phase, or if you take the phase of this combined with the magnitude of this, if you take the phase of Lena and combine with the magnitude of cameraman, cameraman turns out to be Lena, Lena turns out to be a cameraman. That means phase information is very, very important information in a Fourier transform. Now, other than this, with respect to one-dimensional signal, what is the role of the Fourier transform? So what we have to understand here is, here you can see that this is signal 1, this is signal 2. It is a low frequency signal. That means 5 oscillations are there. If you count it, 1, 2, 3, 4, 5. That means 5 oscillations are there. That means the frequency is 5. You can see that exactly there will be a peak at 5 Hertz. Here 10 oscillations are there. That means exactly there will be a peak at 10 Hertz. So how often the frequency of the signal change? In other words, the rate of change of the signal, it is captured by means of a parameter called frequency. Fourier transform gives the frequency content of the signal. This is what we have to understand very clearly. So a very simple idea is, Fourier transform helps us to get the frequency content of the signal. Now this idea, we have explored it in a different way. Now you see that you have this image, which is basically an X-ray image of your hand. Whether this image is visible to all?
Yeah.
Is it visible? Now you see, what is the difference between these two images? Can anyone just comment on this? How this image is different from this one? Any answer?
So dear participants, feel free to ask.
No need to feel free, absolutely, because none of the answer is a wrong answer. None of the question is a wrong question. Everything, feel free to discuss. My thing is, it is a very clean image. But if I add a noise to this image, I'm able to get this one. So this is a clean image. This is a noisy image. Can anyone guess what type of noise it could be? Dear participants, any idea? Whether are you online or?
Yes, sir, they are on online.
Okay. They have a little bit of hesitation. Oh, no need to worry. So this happens because sometimes they may think that if we give wrong answer, what will happen? Some kind of a hesitation will be there always. But my humble request to all the participants is, feel free. It is not again a conventional classroom. This is something we have to discuss, something we have to elaborate, and then we have to work on this. Here, what I want to convey here is, it is a clean image. It is an image which is corrupted by noise. The nature of the noise is basically a sinusoidal pattern. This is what you have to understand. So you can see that there is some kind of a repetency. You can see that repeatedness is there. So this is basically a sinusoidal noise. So what is the difference between these two? I'm sure you'll be able to know. Difference between these two type of noises. Can anyone give answer to this? You have noise free, you have noisy. This is also a noisy. What is the difference between these two? Visually, it is very clear, you know.
Sir, good morning, sir. I am Jagadisan.
Good morning, sir. Feel free to give your answer, sir.
Sir, because of this noise, maybe is synchronizing numbers, sir. Signal number based on.
Yes, sir. Yes, sir. Sir, anything that you can observe between, what is the difference, sir? I'm asking you a very simple question. What is the difference between these two images?
Sir, this is like a television pattern, sir. Television is also like this only.
Okay, sir. Okay, sir.
Signals, sir. But I think in my point, I thought that this is maybe the CRO monitor shows this kind of imaging, sir.
Yes, sir. It's a
CRO
very
monitor
good.
and some advanced technology devices shows clear images, like in the first image. If
yes.
Is it correct, sir?
Yes, sir.
based on CRO type of devices, sir?
Yes, sir. Okay, sir has tried his level best to give an answer, but even though he's giving an analogy, but what we want to highlight here, thank you very much, sir, for giving your answer. The thing is, there is a difference between these two type of images. This is what I want to highlight. Here it is a low frequency. That is what you can see here. The spacing is something, it is distributed. You see here, there is a distribution. Here it is very closely spaced. The noise is very closely spaced. Here there is noise is not closely spaced. Here the frequency is low. Here the frequency is high. This is what we want to highlight. Okay, then how we can minimize this noise? First of all, I should know what type of noise is present in the signal. Now you see classically, this is a noise-free image. If I take Fourier transform, I'll be able to get the power spectrum. This is the power spectrum of my clean image. On the other hand, if I take the power spectrum of this image, I'll be able to get additional 2 peaks. Whether is it visible to all? The difference between these two, is it visible?
Yes, sir, it's visible, sir.
Yeah. So what is the change that you can observe? Along with the central bright spot, you will be having additional 2 spots. Now comes the question, sir, why these 2 spots should come here? That should be the research attitude. If you have a very good research attitude, then the first fundamental question what should come to your mind is, sir, this image is different from this, no doubt about it. This is the power spectrum of this one. This is the power spectrum of this one. Along with the central bright, we will have additional 2 spots. We know very well what is the formula for sine theta? E power j theta minus e power minus j theta by 2j. I hope every one of you knows this fundamental formula. So you have positive frequency, you have negative frequency. So in spatial domain, because of this sinusoidal noise, I'm having 2 additional peaks. So in our power spectrum, if you are able to observe additional 2 peaks, then very well you can say that these 2 peaks, this corresponds to a sinusoidal interference. If you remove this bright spots, then you will be able to get the image like this. So this we call it as denoising. So if this pattern is not appealing to you, if you want to minimize this, then what you are supposed to do, you have to take a rubber and then you have to remove these 2 spots and then you have to take the inverse Fourier transform, you will be able to get this. Colloquially, I'm saying that you need to have a rubber here in order to rub this. If you have a rubber which could eliminate these 2, then you will be able to get this image which is closer to this image. That means you are doing the filtering in the frequency domain. This is very, very important. So how you can do that with a rubber? Instead of a rubber, you have to go for a mask. That's all. So mask will help you to remove this 2 bright spots. So what is more important is whenever you take the power spectrum of your noise, you will be able to identify the periodic noise in the power spectrum. If you are able to remove this and then if you take inverse, you will be able to minimize the impact of the noise. Now we will go for a very interesting discussion. You see that this is the thing. You see that this is the thing. So what is the difference now? Additional to the bright, we have again 2 spots. Why here these 2 are very much separated? You see the previous case, it is closely spaced. You see here, it is very closely spaced, whereas here it is spaced in a farther way. Can anyone guess why it has to be farther spaced in a farther way?
High frequency.
Yeah. So what is more important is high frequency means compression. So compression in time domain, it is equal to expansion in frequency domain. If you can rub these 2 things, you will be able to get your denoised one. So what I want to highlight here is Fourier transform helps us to know whether a periodic noise is present in the given signal or not. So this is another application of the Fourier transform in image processing. So normally, whenever you take Fourier transform, what the faculty used to tell is Fourier transform gives the frequency content of the signal. This is the golden statement that is available in almost all the standard textbook. But if you give to the student like this, what is basically frequency, how it can be explored, what is power spectrum, how you are able to get the additional P. And if you remove this, it can be applied for this application, then the students will be very much motivated to learn this particular Fourier transform. So what is the study that we have done? If you have a sinusoidal pattern in your image, then this sinusoidal pattern, I can able to visualize it in the frequency domain as 2 separate dots. If you have a mechanism which could remove these 2 dots, then you are basically doing denoising operation. That means Fourier transform helps us to know whether any periodic pattern is available in the given image or not. So this is the ultimate idea. Now, even though Fourier transform is very powerful, some of the shortcoming is it is meant for global analysis. It is not for local analysis. So if you want to do local analysis, that means you want to get both time and frequency information, then you have to go for a short time Fourier transform. Now, the drawback of Fourier transform, I can represent in this way. You see here, it is a DC signal. It is a 2 Hertz signal. It is a 10 Hertz signal. If you take the spectrum, then you will have 2 Hertz and 10 Hertz. You see that there is a peak at 2 Hertz. There is a peak at 10 Hertz. Now, this signal 2, what we have done is we have interchanged these two. That means 10 Hertz is appearing first, 2 Hertz is appearing next. That means signal 2 is different from signal 1, but if you take the spectrum, exactly it will be alike. That means I am not able to get the time information. I don't know whether 2 Hertz is appearing first, 10 Hertz is appearing next, or 10 Hertz is appearing first, 2 Hertz is appearing next. From the spectrum, I may not be able to say precisely which frequency is coming first, which frequency is coming next. That is the major drawback of Fourier transform. So Fourier transform, even though it is a very good tool to give the frequency content of the signal, unfortunately, it is not giving any time information. If it is not giving any time information, I may not be able to say which frequency is coming first, which frequency is coming next. That we call it as the instantaneous frequency. If you want to know, then definitely you are in need of a time information. That time information is missing in Fourier transform. Because of that, people have developed short-time Fourier transform. Now, short-time Fourier transform, it is also known as windowed Fourier transform. This is the expression. So if W of t minus tau is equal to 1, then it becomes Fourier transform. So what we are taking here is, we are taking a signal, we are passing it through a window, and then we are taking the Fourier transform, then it becomes short-time Fourier transform. So always the resolution depends on the window size. Now you see here, very easily you will be able to observe the difference. Now you see here, this is signal 1, this is signal 2. So what are all the frequencies that are present? 5 Hertz is present, 15 Hertz is present. Now 5 Hertz is coming first, 15 Hertz is appearing next. What about signal 2? 15 Hertz is appearing first, 5 Hertz is appearing next. That means signal 2 is different from signal 1. If you take only Fourier transform, my spectrum will be alike. That means there is no difference between spectrum of signal 1 and spectrum of signal 2. Is it clear to everyone? Whether you are able to observe the change? Even though my signals are different, my spectrum is alike. That is the problem with Fourier transform. So if you take short time Fourier transform, you can observe that the x-axis is time, the y-axis is frequency. You know very well that 5 Hertz is appearing first, 15 Hertz is appearing next. Whereas in this case, 15 Hertz is appearing first, 5 Hertz is appearing next. That means it gives additional time information. That is the beauty of short time Fourier transform. So Fourier transform, it is not giving any time information, whereas short time Fourier transform, it gives time information along with frequency information. That is the beauty of short time Fourier transform. So what is basically short time Fourier transform? Pass the signal through a window and then take Fourier transform, then it becomes short time Fourier transform. How to choose the window? If your window is very short, it gives very good time resolution. If the window is wide, it will give very good frequency resolution. So if you get very good time resolution, it is very difficult to get good frequency resolution. If you get very good frequency resolution, it is very difficult to get good time resolution. So this we call it as the Heisenberg uncertainty principle, which is very, very common principle in physics. I hope if some of you are from physics background, this term Heisenberg uncertainty principle will not be new to you. Position and momentum of the particle cannot be determined very precisely. That is the fundamental idea given by Heisenberg. The same thing holds good for signal processing. That means it is very difficult to get both time as well as frequency resolution. This is similar to that of quality and quantity. For example, assume that a hotel is popular. For example, most of you may be living in and around Dindukal. Hotel is upcoming. That means the number of customers will be less. They will be providing very quality service. After some time, the hotel becomes very popular. Crowd will coming to that particular hotel, naturally the quantity will be more. Quality, there is every possibility that it may degrade. That is the problem of quality versus quantity. So quality into quantity, it is always a fixed product. Similarly, gain bandwidth product, it is always a constant. Similarly, time resolution, frequency resolution, the product is always a constant. That is the fundamental idea behind Heisenberg uncertainty principle. That is, now comes the question, is it possible to get both good as well as time resolution as well as frequency resolution? The answer is very, very, very difficult. The limitation is given by Heisenberg uncertainty principle. So it is like asking, I want huge sum of money, at the same time I want to be peaceful in my life. Is it possible? Definitely very, very, very difficult. If you have lot of money, you have to answer to the income tax department. They won't allow you to be peaceful. If you have less money, naturally it can be more peaceful. You don't have to answer to anyone in the government. That means money, peacefulness, they are interrelated. Similarly, time, frequency, they are interrelated. Frequency is always inversely proportional to the time. That means if you get very good time resolution, naturally you will be losing the frequency information. So this we call it as Heisenberg uncertainty. Now you see that very simple example. Here my signal is time limited. That means at only one point I'm having a value. Here I'm having the value throughout. If the window length is only short, I'm getting very good time resolution. That means I know exactly that the signal changes here. If your window length is very large, I'll be able to get very good frequency resolution. I know that it is a 10 Hertz signal. That means choice of window decides the resolution in the case of short time Fourier transform. So this is another important thing. The choice of window decides the resolution. But the problem is, once you fix the window, it cannot be stretched or it cannot be compressed. That means you will not be able to get multi-resolution analysis. In the case of short time Fourier transform, you have to go for wavelet transform. So what is basically wavelet? That we will try to address it by just comparing the Fourier transform with short time Fourier transform. So decomposition, you will be doing only frequency decomposition, whereas in short time Fourier transform, you will be able to get both time and frequency information. The basis function is complex exponential in Fourier transform. It is windowed basis function in the case of STFT. Then information in Fourier transform, you will be able to get only frequency information. Here you will be able to get both time as well as frequency information. Fourier transform is a very good tool for stationary signal, whereas it is a very good tool for quasi-stationary signal. So if you want to get time as well as frequency information along with multi-resolution, now comes the question, what is basically multi-resolution? That means multi-resolution, you can think about a mathematical microscope. Through that microscope, you should be able to see both ant as well as an elephant. That is the fundamental idea behind multi-resolution analysis. The transform which can help us to get multi-resolution analysis is basically a wavelet transform. So wavelet transform, the term wavelet, it is originated from the term ondulet. Ondulet is basically a French term which always stands for restricted wave. So the ondulet, because French mathematicians and physicists, they played a very, very important role in the development of wavelet transform. That is the reason why the origin of wavelet is from France. So in France, it is called as ondulet. Ondulet means restricted wave. So what are wavelets? Oscillatory function of finite duration. It is always called as wavelet. So oscillatory function means the average value of the signal should go to 0. Integral minus infinity to infinity. Psi is the general notation for wavelet. If you are not comfortable, you can use f. F of t dt equal to 0. That means the function is oscillatory. If the average value of the signal is 0, naturally it will be oscillating. If you take the energy, if it is finite, then it is basically of finite duration. So the next condition is the admissibility condition. If any wavelet satisfy all these criteria, then it is an eligible candidate for wavelet transform. Now comes, there are two classes, continuous wavelet transform and then discrete wavelet transform. So just understand that there are two classes. There are some drawbacks of continuous wavelet transform like redundancy. So in order to overcome the redundancy, people have developed discrete wavelet transform. So scaling and shifting it is the two fundamental aspect in continuous wavelet transform. Since it is being done continuously, it is called redundant representation. I hope every participants know the meaning of the term redundancy. Are you familiar with the term redundancy? Or you want me to explain the term redundancy? Are you familiar with the term redundancy?
It's
Yes, sir.
unwanted information, general.
Yeah, additional or madam has rightly said additional or unwanted. For example, you can see the students coming to the examination with more than 2 pens. Even 1 pen is sufficient to write the examination, but students in general, I'm talking about old students, not the current students, right? In our age, I'm talking about, they will come to the examination hall with 2 pen, minimum 2 pen. Am I right? So what is the purpose of redundancy there? Safety. Whenever you have redundancy, safety is assured. For example, a train is about to leave the station. What are all the signals that you can find? A signal changes from red light to green light. Second thing, a whistle will be blown. Third thing, you can see the engine sound. The train is about to start. You can get some announcement also. So announcement is also conveying the same meaning. Change of signal is also conveying the same meaning. And then whistle sound is also conveying the same meaning. That means it is called as a redundancy. Redundancy is always for safety. This is what you have to understand. Redundancy is not something unwanted. Most of the people used to think that redundancy is unwanted. Absolutely not. In some time, redundancy is required for safety. So redundancy means additional. For example, you are writing your thesis. You are doing chapter wise. Chapter 1, chapter 2, chapter 3, you are framing. You know very well that you will be saving it in different hard disk. You will be saving it in your hard disk in a computer. You will be saving it in your laptop, and then you will be saving it into a for hard disk. That we call it as a redundancy. All these three represents the same chapter, but we are doing a copying of the original thing. That copying is basically called as redundancy. Why we have to do that process? Because we want our data to be safe. Whenever you want to ensure safety, definitely redundancy is a must. But whenever you don't want the redundancy, you have to overcome this. But what is the more problem with redundancy? Additional space you have to utilize. So how to overcome that redundancy? It is called compression. Later on, we will discuss about this. Time being, understand that redundancy means additional information. Always the fundamental goal of the redundancy is for safety. Now, wavelet decomposition. What is basically wavelet decomposition? That I will try to illustrate by means of a very simple diagram. S stands for signal. You are doing decomposition into approximation and detail. Then in the approximation, you are splitting into approximation detail. And then in this approximation, you are doing this decomposition. This we call it as the wavelet decomposition. So just imagine this signal as a onion. Okay. I hope all of you will be aware of this onion. Now the price is going in a exponentially increasing manner. There are two types of onion. One is a small onion and another one is a big onion. I hope everyone knows this, So this signal S is a big onion. First you do what you are doing is you are peeling off the outer layer of the onion so that remaining onion you call it as approximation. The outermost layer you call it as detail. Now I want to peel the onion means whatever remaining thing you have that you are peeling the outermost layer that we call it as D2, and whatever has left it is A2. Now you peel off the outermost layer that we call it as D3, whatever is remaining that is called A3. So this wavelet decomposition is similar to that of peeling of the onion. So onion, we are used to remove the layer of the onion, that I'm calling it as the peeling operation. So this operation is similar to that of the wavelet decomposition. Now you see that this is the onion that you have, which is basically a signal which consists of some values. Now how to go for approximation, how to go for detail. Now we will try to illustrate this. It is basically an addition. What we have done, I have simply added this two value and then I have divided by 2, and then you will be able to get this first approximation. Now what is happening? There is a shift. Now I'm taking the next two samples and then I'm dividing it by 2. We are getting the next approximation. Then you are shifting it. You are going for addition and then divide by 2. Then this operation, you are getting this. So what is the length of the signal? 1, 2, 3, 4, 5, 6, 7, 8. So you are getting 4 approximation values. Now how to get the detail? Just you see that you are taking this sample and then you are taking the difference. Instead of addition, you are taking the difference. The value is -1. So you are taking the difference. You are taking it. So now what you can get is you are getting 4 approximation, 4 detail. What is more important here is here the values goes on increasing, here the value goes on decreasing. So here we know very well that successive decomposition should be done only on the approximation. Now you do one level. So this I'm retaining as such, and then I'm doing this 3, 7. If you add and divide by 2, you'll be getting this 11 and 15. This is your approximation. Now you difference it. This becomes the detail. Now you take the difference, this becomes the detail. So you are taking sum and then you are taking the difference. That I'm calling it as the approximation and detail. So if you do this, you will be able to get this. So how many levels that I have to go for? That depends on the length of the signal. Here it is 1, 2, 3, 4, 5, 6, 7, 8. So 8 samples are there. Log of 2 power 3 is 8. So you can go for 3-level decomposition. So you will be able to get this as your approximation and this as your detail. What you can observe here is the value goes on increasing in the approximation type and the value goes on decreasing in the detail. So approximation is basically low pass filter. Detail is basically high pass filter. So here after in signal processing term, this operation I'm calling it as low pass filter and high pass filter. That means whenever you want to implement wavelet transform, you have to do low pass filtering option and the high pass filtering option. That is, any difficulty till now? Any questions? Whether you are able to understand the view or you find it too tough? I mean, going in a fast way. Participants feel free. Is it understandable? Any queries? Any difficulty, any queries in between, any doubts?
Audience?
Some of our participants in chat are saying that you are going in perfect speed and they're requesting you to go a little bit slow, sir.
Closer.
Sure, ma'am. Sure, ma'am. So whatever feedback the participants give, we will follow it as per their requirement.
Okay, sir.
So what is
Thank you,
more important? What is that I want to convey here? Let me summarize it. So the participant should understand that transform helps us to explore the signal. That is the first point I want to highlight. What do you mean by exploration? I want to get additional information from the signal. That is the fundamental goal of taking transform. Let me give you a very practical scenario. How many participants are from teaching field? Whether all of them are from teaching field, that is faculty, or anyone from non-teaching, other than teaching. Most of you are from teaching profession, am I right? At least you might have indulged in at least 1 or 2 years of teaching. Let me assume like that. Shall I assume like that?
Yes, sir. Yes, sir. Absolutely, sir.
Okay. In your campus, you may had the opportunity of taking students for an excursion. Am I right? Taking the students outside the campus. Either you call it as your tour or industrial visit or some kind of an excursion, whatever may be the name. I hope you might have experienced it. It is one of the toughest job. I'm sure those who have taken the students outside their campus, they will realize it. Is it right, sir? Whatever may be the college, very, very challenging task to take the student outside the campus, visit a place, and then come back to the same campus safely. That is the ultimate objective of any industrial visit or tour or some kind of an excursion. Is it right, sir?
Yes, sir. Yes, sir.
Because ultimately we want to ensure the safety of the students. You might have observed that a student who is very polite in the classroom, his behavior may be totally different other than the campus. Is it right? If you take the student, for example, you are in Dindikal, you are taking the students to Ooty. In Ooty, the student behavior will be totally different. You might have observed it. I'm sure many of you. Is it the same student whom I'm seeing it in the class? Such kind of a exclamation you might have got it. Am I right?
Yes, sir. Yes, sir.
So
Sure.
the signal is now the student. The student behavior inside the class need not be the same as student behavior outside the class. Is it right? That means the signal remains the same. That is the student. Inside the class, it is called a time domain. Outside the class, I'm calling it as the frequency domain. So you may observe that a student who is very studious, very polite in the classroom, totally his behavior will be different if you take him outside the classroom. Some students who are not good in studies, they will be very much cooperative in the two. This kind of experience, I'm sure you might have got it. If you take the students outside the campus, such kind of experience you will gain. So what I want to convey here is, you just assume the student as the signal. Now, if the student is inside the class, you are retaining him in a particular domain that I'm calling it as the time domain. If you take the student, that is the signal, to some other spot other than the classroom, then I'm calling it as the frequency domain. So you can very well observe the change in behavior of the student. Even though the signal remains the same, the characteristics will be totally different. That means I'm able to get more information about the student if I take it other than the classroom. So the same thing we are doing it with respect to signal also. As long as the signal is in the time domain, I may not be able to get much information about the signal. So if you take the signal to the frequency domain, you will be able to know how the signal changes with respect to time. What are all its important characteristics? So this is what I want to convey here. In that, we have Fourier transform, which gives only frequency information. But if you want both time and frequency information, you have to go for short time Fourier transform. But if we want to do multi-resolution analysis, you have to go for wavelet transform. So these are all the three classes of transforms we have visited. So wavelet is basically implemented by means of a filter bank like this. So if you are from an electronics background, then this will not be new to you. If you are from some other background, just leave this, because don't try to understand it. It may not be so easy. Because what you call it as a filter bank, here you see that H0, H1, G0, G1, they are called as filters. This is called analysis filter. This is called synthesis filter. So proper arrangement of analysis and synthesis filter, it is always called as the filter bank. So what is basically bank? Group of something, we call it as the bank. So filter bank means group of filters arranged in a specific fashion. We call it as the filter bank. For this input signal, there are two paths for the input signal. Hence, we call it as the two-channel filter bank. There are different kinds of filter bank like two-channel, M-channel like that. Here we call it as the two-channel filter bank. Through two-channel filter bank, we can implement the wavelet transform. This is what we have to understand. So if you do it for image, you have to do it for row processing followed by the column processing. So image is basically a matrix which has got rows and columns. So if you want to extend this wavelet for image, you have to do both row processing followed by column processing. This is what we want to highlight. So this thing, I'm just skipping it because it will be somewhat difficult to you. So what I want to highlight here is this. Let me illustrate it by a very simple idea. So this thing may not be helpful. Now you see that if you do wavelet decomposition, here all are 1, the remaining are all 0. This information, it is packing to low frequency. So you see here, this band is having all the information, whereas all the other bands, they don't have any information. So if you do second level, then this will be the information. This is what you can get it by means of a filter bank. So here you are able to separate the signal into different frequency band. That is the ultimate objective of the wavelet transform. So whenever you take the wavelets, wavelet filters play a very important role. The filters have to be very short so that computationally it can be efficient. Then it has to be symmetric so that my storage space will be minimized. Then it should have very less number of vanishing moment and then regularity. So how to choose a wavelet for specific application? These are all the guidelines. So if my wavelet is symmetric, naturally I will be able to get a linear phase. If my wavelet is compact, then computation can be done very easily. If my wavelet is regular, then a periodic pattern I will be able to get. So these are all the criteria for choosing the wavelength. So for what application I can go for? Let me do it in a very simple way so that every one of you will be able to understand this. So I hope everyone will be doing washing, right? So how I can understand the denoising by means of a phenomenon called washing, we'll try to understand this. So what is basically noise? Noise is basically a unwanted information. It occurs either during acquisition, storage, or transmission. The major challenge in denoising is how I can preserve the information by removing the unwanted information. So this I can understand, or this we can illustrate by means of understanding different types of noises that are there in the biomedical signal. If you take ECG, the common interferences, power line interference and baseline wandering. In EEG, it is called eye blinking. In ultrasound image, we have speckle noise, where in MRI image, region noise. That means different types of biomedical signals are affected by different types of noises. So how I can minimize this noise? Now you see that there are green dots as well as there are red dots. Whether all of you, is it possible to observe these two? Green means I want to retain. Red means I want to throw away. So green dots correspond to signal and red dots correspond to noise. What is the goal now? I want to separate the signal from the noise. So what I have to do? I want to separate the green from the red. So how to do this and how to throw away this red? That is the ultimate idea of image denoising. Now we will try to understand the analogy between washing and denoising. I hope everyone will be very much familiar with washing. What are all the few steps involved in washing? Can anyone give the answer? Washing of clothes. Whenever you want to do washing, for example, you have a dirt shirt, which is dirt. I want to wash the clothes without using washing machine. What are all the steps involved in washing? Can anyone just give the idea? No one knows washing?
Hand wash, sir.
Huh?
Yeah.
Yes. What is the first step in washing? You can give any step.
Is it rinsing, sir?
Yeah, very good. Rinsing. Second, rubbing. Rubbing. We have to wash it with a soap. Assume that you are doing it by hand. Then rubbing. What is the third step? No idea? Drying. Drying plays a very important role. That is the last. I will try to give it. Assume, what is this? You can observe. This is a shirt that is blue in color. Unfortunately, coffee or something being split into it. Tea or coffee, it is a brown in color. Now you understand this logic. Shirt is my signal. This dirt is a noise. Now I want to remove this noise. So what you have to do, as Sir has rightly mentioned, soaking is the first step. That means I want to take the shirt from air medium to water medium. This is the fundamental thing you have to understand. I want to take the shirt from air to water. There are different classes of water available. I hope you know this. Either you can do it with groundwater, or you can do it with the corporation water, or you can do it with hot water, whatever it may be. That means you are transforming the signal from time domain to frequency domain. What is time domain? Air. What is the frequency domain? Water. Is it clear now? Any difficulty?
No,
Now,
sir.
after soaking, what you should do? Rubbing. Rubbing only removes the stain in the cloth. Is it right? I hope everyone will understand this. After rubbing, I cannot put my shirt directly. I have to dry and then I want to take it. So what you have here is a shirt with dirt. What you have is basically a clean shirt. So this we call it as washing. The same thing with respect to denoising. If you understand this analogy, then denoising is very, very easy. Now you understand this, you have an image. It is basically an ultrasound image. Unfortunately, this is similar to that of this shirt. This image is corrupted by noise. What I have to do is, I want to take this from the spatial domain to frequency domain. This is similar to that of a soaking, that we call it as the forward transform. Then you have rubbing. So instead of rubbing, what we have is the thresholding operation. Thresholding will retain some coefficient and then it will throw away some of the coefficient. That is similar to that of a rubbing. After that, I have to take the inverse transform, and then I want to get back to my original. Now you see that this image is corrupted by a speckle noise. That noise has been minimized here. So here I cannot say whether it is liver image or not. Here I can very well say that it is a liver image. That means I can preserve the information as well as I can minimize the noise in the signal. Now whether you got a clarity with respect to this analogy? Any doubt? If you have any doubt, feel free to interact with me. What is more important is whenever I do washing, I want to move the signal from one domain to another domain. That is air domain to water domain. And then I want to do water to air. This I am calling it as drying. This if we call it as soaking, this we call it as drying. So soaking is similar to that of forward transform. Drying is similar to that of a inverse transform. But in between this soaking and drying, you have to do a very powerful nonlinear operation, which is basically rubbing. Why I am calling it as nonlinear? Can anyone guess why rubbing is called as nonlinear process? You can unmute yourself and then you can discuss why it is called as non-linear. Because rubbing I will be doing based upon the intensity of the noise, that is intensity of the whatever stain I have in my cloth. So if more stain is there, I will be doing more rubbing. If the stain is less, I will be doing less rubbing. That means it is not uniform always. It is depending upon the type of the stain that my shirt has. Similarly, thresholding, I cannot do it uniformly. I have to vary with respect to the intensity of my noisy pixel. That is the reason why it is called as non-linear operation. So forward transform is a linear operation. Inverse transform is a linear operation, whereas thresholding is a non-linear operation. So this is what one of my PhD student has done it. So this is the PhD work of a student. Unfortunately, I have given a similarity with respect to washing. If he watches this lecture, then he will be very much upset. Sir, I have done a lot of work for 3 to 4 years, and then you are just giving an analogy equal to that of a washing. Just for fun, I have given this analogy, but this is also true in some sense. So what you can do is, as a researcher, sir, I want to do denicing. So you can change the water. Different types of waters are there. Similarly, you have different types of transform. Either I can go for wavelet transform, wavelet packet transform, contourlet transform, or I can go for a multi-wavelet transform, or you can go for a tunable Q factor wavelet transform, etc., or quaternarian wavelet transform like that. You can also go for thresholding. So different types of thresholdings are available, starting from very basic thresholding to shrinkage techniques, advanced shrinkage techniques. So one of my PhD student, his name is Dr. C. Vimal Raj, who explored on this. I will try to give his work in a very summary form after this talk. So here you can see that this is the noisy signal. You are taking forward transform, which is similar to that of soaking. You are doing denoising operation, which is called thresholding, and then you are doing inverse transform in order to get this signal. So this is the fundamental idea that we have to understand. So this thresholding, there are different types, hard or soft thresholding. So which one to apply? Naturally, it depends upon the nature of the noise as well as which will preserve the information. In general, soft thresholding is preferred over the hard thresholding. Now we will try to compare these different transforms. So basis function is complex exponential. Here it is the mother wavelet. So continuous transform, this is the expression. Then time is transformed to amplitude and phase in Fourier transform. It is transformed as amplitude and scale in wavelet transform. Here we will be able to get very good time resolution. Here also I'll be able to get time resolution. Here I may not be able to get any time information. Here definitely I will be able to get both time as well as frequency information. So this is the computational complexity, which is very less in the case of wavelet transform. That is the reason why it is widely explored by researchers. So another transform is basically a cosine transform. Every Indian must be proud of discrete cosine transform because it was developed by 3 Indians. Those 3 Indians are Ahmad, Rao, and Natarajan. Ahmad, Rao, and Natarajan, they developed discrete cosine transform. Just this is Ahmad, this is Rao, and this is Natarajan. Very easily you can observe that these three are Indians. This transform, it had the ability to overthrow Fourier transform with respect to compression. You see, Indians have contributed a lot in the development of the transform. Unfortunately, we Indians, we won't appreciate our own forefathers. That is the problem. That is the reason why even discrete cosine transform, it may not be there in the syllabus. So if Fourier transform will be there in the syllabus of DSP, but unfortunately we won't keep DCT. So my request to all the academic experts, at least you try to give an overview of DCT whenever you have an opportunity to serve as a board of studies member. Because as Indians, we have to be very proud that this DCT was developed by 3 Indians. You see that there is unity in diversity. Ahmad, Rao, and Natarajan, their name speaks for themselves. There is again unity among diversity. Natarajan happens to be the PhD student of Professor Ahmad. He seems to be excellent in coding, and Rao happened to be the colleague of Ahmad. These three together, they developed discrete cosine transform, which has got very good energy compaction. The reason for the popularity of discrete cosine transform is that it is real in nature. It is not complex in nature. For example, Fourier transform is complex in nature, whereas your discrete cosine transform is real in nature. If you take image, definitely it cannot be complex. It is a real quantity. All the pixel values, it will not be complex. For example, you are going to a shop. You want to buy 1 kg of rice. You cannot go there and ask for 1 plus J0 kilogram of rice. The shopkeeper will say that the man has got mad. Is it right? So all real world quantities, whatever you take, it is not complex in nature. For example, your blood pressure, whether your blood pressure is complex or real. Is it real or complex quantity?
Real.
It is a number. End of the day, that number is a real number. It cannot be complex. For example, temperature of your body, whether it is Fahrenheit or Celsius, whether it is real or complex.
Real, sir.
Real. You take BP, that is heartbeat, this much beat per minute, whether it is real or complex.
Real number.
Again, it is real number. If you take any quantity, it will not be complex in nature. So that is the reason why I need a complex quantity to represent a real quantity. That idea motivated Ahmad to develop discrete cosine transform. But believe me, why these people were very aggressive to develop discrete cosine transform was Ahmad write a proposal to US funding agency regarding the development of a new transform. But unfortunately, the funding agency rejected the proposal of Ahmad. That hindered him to develop this discrete cosine transform, and he made it world famous. Whatever image you are seeing, it is in JPEG format. Inside the JPEG format, DCT is playing a very, very vital role. What we have to understand is, whenever people develop some novel things, always their work will be rejected. People will not be able to understand and appreciate. See here, Fourier work was rejected earlier. Nowadays, it is used in wide varieties of field. Similarly, Ahmad work was rejected by US funding agency. Now it is worldwide, it has got recognition. Similarly, if you write a paper and if it gets rejected in a journal, don't worry. In future, it may do wonders. Who knows? That is the reason why whenever a PhD student comes to me, if he or she is very sad, sir, I have sent it to a journal. Within half an hour, it got rejected from my editor. I don't know what to do. Then I will say that even Fourier work was rejected, Ahmad work was rejected. We are nothing in front of those. So if your work is rejected, who knows, one day you may become Fourier or you may become Ahmad. So always keep it in mind that if your work is rejected, just go through the work, see what is the drawback in that work, and then try to explore. Definitely you can publish it in a fantastic journal. So that should be the spirit we should have. So discrete cosine transform. So the beauty, let me tell it, it is a real transform. In one way, in one word, I want to tell the beauty of DCT is it is a real transform. We know very well that cosine functions are even symmetric. Cos of minus theta is equal to cos theta. That means it is a symmetric transform. So energy compaction, very good energy compaction. So it is widely used in JPEG standard. The last, ma'am, how much minute is left? Till what time I should take, ma'am?
Sir, actually up to 11. No problem, sir. Carry on.
Maybe the next speaker may be waiting, ma'am.
7:30, sir. Actually. There is some
Whether I have to continue or can I stop? This is as per your convenience. We can have as per participants' view. We can, if you want, I can continue. Or if the other speaker or if the participants also want some break, then we can wind up. Based upon their choice, we can do.
Sir, 11:50 we can wind up, sir.
Okay, ma'am. Sure. We will stick on to 11:15.
Yes,
So
sir.
compression is another area where I did my research. Always it is basically a compact representation. So I want to do compression because of two things. I want to represent the signal with minimum number of bits for effective storage and efficient transmission. So this is the fundamental idea. This I will try to give the motivation. So here nowadays telemetry, everything is gaining momentum. That means online patient monitoring, offline patient monitoring, all these things are gaining momentum. So if you have a radiography X-ray, if you take the X-ray of a chest, this is occupying this much space. If it is an ultrasound, it is occupying this much. If it is a PET, then it is occupying this much space. What is meaning? We want to store all this information with the reduced number of bits. So this can be done by means of compression. So the fundamental idea behind compression is only one thing. That is, all the data will not convey useful information. I can classify the data into useful data and unwanted data. That unwanted data we are classifying into two types. One is redundant and the other one is irrelevant. So always there is a difference between redundancy and irrelevancy. So redundant means duplicated data. Irrelevant data means unwanted data. So noise can be irrelevant, whereas redundancy is duplication. So this difference we should know. For example, what is irrelevant? I'm here to talk about compression. Instead of talking about compression, if I talk about myself, what is my name, age, whether I'm married, not, what is my profession, all those things, if I go on explain, then it becomes irrelevant. So this is what irrelevant is all about. So what is very important is, if you have a data, if you can minimize these two, then definitely you can achieve compression. So redundancy you have to minimize, irrelevancy you have to throw out, so that you will be able to achieve compression. Now you will try to understand this by a simple diagram. What is that you can see here? Can anyone answer this? It's closer to lunchtime, so I'm sure you will be like to have this kind of a drink. So what is this?
Orange.
Very good, ma'am. Exactly correct. It is an orange. We know very well that orange cannot be easily taken from one place to another place. So what we are doing it, we are taking a juice of it, and then we are drying it as far as possible in order to make it as a powder, so that very easily I can transmit from one place to another place. At the receiving end, whatever I have taken out, I'm going to add it so that I'll be able to have it as a drink. So this is the fundamental idea. So whatever I'm removing it at the transmitter end, that same thing I want to add it at the receiver end, so that I'll be able to get the original information. So this is the fundamental idea behind compression, that works on only one principle. I want to minimize the redundancy. So there is a redundancy, you can classify into three categories. One is spatial redundancy, that is successive pixels are alike, that we call it as the spatial redundancy. Psychovisual redundancy means always there is a limitation in human eye. That means human eye can see information from 4000 Armstrong to 7800 Armstrong, that we call it as the visible range. And how effectively I can do the coding, we call it as the coding redundancy. So if you can minimize this type of redundancy, definitely you will be able to achieve compression. So this is the idea behind compression. From the original data, you are getting the compressed data. From the compressed data, if you can get back to your original data, then it is called as lossless compression. From the compressed data, you are not able to get back to your original data, then it becomes lossy compression. For all biomedical applications, mostly lossless compression is preferable. So this is the fundamental idea behind compression. Now you see that we have a transform, we have an inverse transform, and in between that I'm having a quantization. So in denoising, I'm calling it as thresholding. In image compression, I'm calling it as the quantization. So this is the only step behind denoising and compression. So what is the step in between forward and inverse transform? thresholding in denicing. If I replace thresholding by quantization, then it becomes transform coding or transform based compression. Now, what is basically quantization? Can anyone give the idea behind quantization? No idea? It is basically an approximation mapping large set of value to a smaller set of value. It is always a quantization. Now you see this classic example. Nowadays, almost all the educational institutions, grading systems are followed. If a person is scoring between 90 to 100, S grade, 80 to 89, A grade. But from the grade, I cannot come back to the mark. That is the drawback. It is called as many to one mapping. This is the classic example for quantization. This we can broadly classify into two types: scalar quantization, vector quantization. If we are employing wavelet, then it becomes embedded quantization. So quantization plays a very, very important role in compression, similar to that of thresholding, which plays a very, very important role for denoising. So quantization, there are two types, scalar and vector. In scalar, you have uniform and then non-uniform quantization. There are different varieties of vector quantization, which we call it as tree structure vector quantization, multi-stage vector quantization, hierarchical vector quantization. So many classifications are there. Just I want to give a overview. So if you can do some good work, definitely you will be having a bright future. The drawback with JPEG compression is like this. Can you see the difference between these two images? Here it is an artifact, which is called as blocking artifact. So this is the fundamental drawback of using DCT. So if you use wavelet transform instead of this, then this kind of problem will be avoided. So I think I can give one research. These things we can go for it. What is the research work that we have done it in our lab that I want to highlight? First research work is with respect to despeckling of ultrasound image. If you have images which is corrupted by noise, how to remove the noise from the ultrasound image? So one of my research scholar has completed his research work with respect to this. The other research work what we have done is computer diagnosis of diabetic retinopathy using machine learning approach. Then now we are doing additional work with respect to deep learning approach. So speckle is a problem. So if you take ultrasound image, speckle is basically a noisy pattern, which is multiplicative noise. So one of my research scholar who did a work related to this despeckling. There are different types of filters available as linear, non-linear. And then what he employed is wavelet based speckle reduction. His work I'm just summarizing here. So you see here, this is the thing. This is similar to that of washing. So you have a shirt with dirt. You are taking it in the wavelet transform. Then you are doing rubbing there. And then you are taking inverse transform. And then you are able to get the denoised image. So whenever you do a good research, you are in need of a data set. So my humble request to all the participants is first identify the modality in which you are going to work. Then try to get the data set. If it is a real-time data set, it's well and good. Fortunately, we have a medical college associated with respect to our organization, which is called the PhD Institute of Medical Science and Research. From there, we got a lot of data set, but for using it, we are supposed to get the ethical clearance. For this, we are doing this. This is the result of his work. So what he did is wavelet packet transform, and then he performed the thresholding and then inverse wavelet transform. And this is the result that we got it for different set of filters. You see here, this is a original noise free. This is a noisy image. And if I apply SNN, that is symmetric neighborhood filter, symmetric nearest neighbor, that is called SNN, then Lee, and then wavelet, and then the proposed method, you can see that the noise is removed in this case. So, and this work was published in a very good journal, that is Ultrasound in Medicine and Biology, which is basically a LCVA journal. We extended this work using wavelet packet. This is the idea he has done it, and you can see that the result is totally different. And this work we are able to publish in IET Computer Vision. So my request is, another work is with respect to diabetic retinopathy and glaucoma detection. So this work also we are able to publish it in a reputed journal. But not my request to all the participants. So this is the work. I don't want to get into the detail because of time limitation. So what are all the important steps that you have to do? So just I want to summarize this. With that, I will wind up. First one is identify the modality, whether you are going to work with ultrasound, whether you are going to work with CT or MRI or PET, like that you have to identify the modality. If it is a one dimension, whether it is ECG, EEG, EMG, or which type of modality I'm going to work, what type of challenging problem available there. Very important thing is there are two types of data. One we call it as standard data, the other one is clinical data set. If you are using a clinical data set, it is a very, very important thing that you have to get the ethical clearance certificate. Without ethical clearance certificate, your work will not be published in reputed journal. Some time is required to get this ethical clearance certificate from reputed medical hospitals, whether it is Aravind Eye Hospital or whether it is PhD Institute of Medical Science. So there a separate cell is there where they can give the ethical clearance. After getting the ethical clearance, go through what are all the novel methods that are there to attack that particular problem. Then identify the latest algorithm. Then very important thing is modify the algorithm. Otherwise, the work will not be accepted. Then the next thing is if you are getting a promising result, my humble request is try to attack reputed journals. First itself, you have to go for reputed journal. Lot of comments will be given. There is every possibility that the work will be rejected. No problem at all. That input will help you to modify the work. So this is what I want to convey to you. So what is basically ethical clearance certificate? If you have a query to this, then this is the answer. You see that it is PhD Institute of Medical Science, Institutional Human Ethics Committee. This committee will be formed and I am supposed to present what is the work that I am going to do and what type of data I'm going to collect, whether I have to meet the patient or not. All these things I have to present it in front of all these doctors. You see here, lot of doctors are there, clinicians, cardiologists, obstetrician, so many doctors will be there. It will be like a mini viva. They will be asking too many questions. We are supposed to answer the question. If they are satisfied, then they will be giving this ethical clearance. It doesn't mean that I'm working in PSG, they should give ethical clearance. Definitely not like that. If our way of talking is not convincing, then definitely they won't give the ethical clearance. Once you get the ethical clearance, it will be meant for 1 year, then it will be extended. So my request is, if you are doing it in biomedical field, definitely you have to get the ethical clearance. Some journals, it is a must that you have to upload this ethical clearance. So with this, I think I can wind up this with a set of references. Thank you very much for your patient listening. Any doubt, feel free to discuss with me. Always you can contact me for any help. My email ID, I think I can share it with you. So if you want any help, directly you can contact me through my email ID. I'm just writing my email ID. sekirajan@gmail.com. So this is my email ID. Whether this is visible to you?
No, sir.
Okay, ESAKKIRAJAN@gmail.com. So any different, any questions or something like that, feel free to discuss. Whether any doubt with respect to the presentation?
Sir, I am M. Balamurugan, Assistant Professor in Kerala College of Engineering, sir.
Yes, sir.
Your presentation is very good, sir. Easily understandable by real-time examples with no noise. Okay, thank you, sir. Thank you very much.
Thank you, sir. Thank you very much. Anybody who is doing research, definitely feel free to discuss with me for any kind of data set or something like that, any kind of algorithm or whatever MATLAB codes, whatever thing you want to discuss with it, feel free to discuss with us. Thank you, ma'am. Thank you. I wish to thank the organizers again for giving me the opportunity to interact with you all. Thank you, one and all.
Thank you, sir. Thank you, sir.
Okay, sir.
Sriram, sir, proceed.
Okay, ma'am. Okay, ma'am. Good morning, participants. It's indeed a great pleasure for me to deliver the vote of thanks. That was a marvelous session. On the behalf of the Department of Biomedical Engineering, PSNA College Engineering, and on the behalf of the participants as well, I would like to thank Dr. Isaki Rajan, Professor from the Instrumentation and Control Engineering Department, PSG College of Tech, Coimbatore, for delivering such a wonderful lecture on signal processing. Sincerely, I never knew one could make signal processing this very interesting. Hats off to you, sir. Thank you. We were almost floored by your presentation. Thank you very much, sir.
Thank you very much, sir. Yes.
Okay, sir. It's a pleasure, sir.
Yes, sir. Thank you, sir.
We are having a very small break. You can just have a small break and we can join us again by 11:30. Is it, ma'am? Sudha, ma'am?
Yes, sir. Yes, sir.
11:30 for the second session. So we hope to have another breathtaking session from another quality speaker. Hope to see you back by 11:30. Thank you. We can break. Thank you, sir. Thank you.
Thank you, sir. Thank you very much.
Thank you, sir. Thank you very much, sir.
Thank you. Shall I leave the meeting, ma'am?
Yes, ma'am.
Yes, ma'am.
Yes, sir. Yes, sir. Yes, sir.
Okay.
Thank you, sir. Ma'am, good morning, ma'am.
Good morning, ma'am. Am I audible?
Yes, ma'am. Yes, ma'am. You're audible.
Yes, madam.
Ma'am, wait for 2 or 3 minutes, ma'am.
Okay, ma'am. Sure.
Joining actually participants.
Okay.
We'll start, ma'am.
Okay, ma'am.
So good morning, all. It is giving me immense pleasure to invite the guest speaker of this session, Dr. K. Suganya Devi, Assistant Professor, the Department of Computer Science and Engineering, National Institute of Technology, Silchar, Assam. Dr. K. Suganya Devi has done her PhD in video segmentation and pattern recognition at Anna University, Chennai, Tamil Nadu in 2014. She was the gold medalist in MTech from Anna University, Chennai during 2008. She has received many laurels and awards for her meritorious academic performance right from her childhood. She further had a research in artificial intelligence, in particular image processing, medical image processing, along with her career as assistant professor at Anna University. She has received Young Women Achiever Award from Anna University for her able leadership and administration. As a part of her research, she has collaborations with international scientists from France and Malaysia. She has published more than 50 publications in SCA journals and international conferences. She has, to her credit, filed 3 patents in the field of image processing. She has received fund for her research in the name of a sponsored research project from UGC. And 10 students are pursuing PhD under her able guidance. And also 2 of books, one C and another on Python, has gained much fan among engineering students. And also she has published notably 5 books with nationally acclaimed publishers. With this brief introduction about Suganya Devi, ma'am, I hand over the session to ma'am. Thank you, ma'am.
Okay. Thank you for your nice introduction, ma'am, Sudha ma'am.
Thank you.
So, my brief intro is I am Dr. K. Suganya Devi, produced by my parents and directed by my husband. As the producer and director goes in hand, this movie is running successfully and I am standing before you, right? So at the outset, I would like to congratulate the entire team, right from respected chairman, respected principal of this PSNA college, and Professor Jayanti ma'am, Sudha ma'am, and their entire team for organizing this 1-week AECT Sttp program on a wonderful topic, biosensors, medical imaging, and signal processing techniques for disease diagnosis. Actually, this is the need of the hour. And also, I would like to thank for this opportunity to share a few words on the same. Okay. Thank you. Happy morning to all. Shall I share my screen?
Yes, ma'am. Yes, ma'am. Yes, ma'am. It is visible, ma'am.
Okay. So, share sound. Right. So, let me start with this. So, I hope this is known to everyone. If the session is interactive, I will be very happy. This is known to everyone. What is this?
Movie name.
Movie name. Okay. What is the movie?
Final Destination.
Final Destination. I think so. It is having some 5-7 series, I think so, if I am correct. So, what is this Final Destination? What is the common in this? Right from 1, 2, 3, 4, 5, 6.
It is looking like horror.
Horror. Okay. So, horror is the one thing we find in common, but the ultimate is this one, death. That is, the nature has a pattern or design. This is the common in all the series of this Final Destination. It is showing the nature, that is, the death has a pattern. It is already designed and it has a pattern. Okay, so my today's talk is going to revolve around this pattern recognition and how it can be done in the medical imaging and what are the different medical imaging modalities. Okay, so before entering into any topic, my husband used to tell in the classes and in any of the things, he used to tell, before you want to learn anything, or if before you want to learn any technology or subject or anything, you have to love it first. Then only you can learn the things to our extent. Okay, so the technology begins with a love for you. And not only this, so if you want to learn any technology or any subject, we should need the in-depth knowledge on this by having a proper literature. So this is the very good saying of Isaac Newton, that if I have seen further, it is by standing on the shoulders of giants. Right? So this is, so the shoulders of giants are nothing but our ancestors. It may be our ancestors, or it may be our ancient era, or it may be our books or papers or anything. Okay, so we are standing on the shoulders of giants, and then only we can do our research. Okay, so my today's talk will be revolving around these topics. So what is a pattern, and what is the medical imaging modalities, overview of those things, and pattern recognition methods, and interesting examples. So what is this? I hope my screen is visible. Okay, so what is this? These are nothing but natural patterns, right? So if you take the peacock's feather, it will be like this only. The color distribution will be like this, and it will be having the structure like this, right? Even for the honeybee, it is having the honeybee, that is beehive. It is having the hexagon pattern, and even our universe, the Milky Way galaxy, it is also having a pattern from leaf. These are all the patterns that are available in the nature. That is called natural patterns, right? So what it might be? I think so you can easily guess what it might be. The monkey is somewhat screaming, and the dog is taking the stick and it is coming, and the deers are fighting with their horns. These are some, yes, no, this is some of behavioral patterns. So the monkey will behave like this only. It will scream like this, and it will itch like this. And the dog, if I am throwing anything, based on the training, it will be picking up the stick or whatever may be the object. So it is nothing but the behavioral pattern. All the animals, not all the animals, all the human beings, the living organisms in the universe, it is having the behavioral patterns. Say for example, I will behave like this, everyone will be having the behavioral patterns, right? So obviously this is musical patterns, and music, all the music is revolving around that sarigama padanisa, right? That seven swaram, you will be calling it as seven swaram. So that is also a pattern. Likewise, we are having the patterns unknowingly or knowingly in our images too. Whatever may be there, say, I am specialized in medical imaging, not only medical imaging, image processing. So today I am going to deliver the things on medical imaging. So I have taken the medical images. Okay, so this is the medical imaging patterns. Every images it is having pattern in it, right? So this even the primary school students, they are coming across these things. I hope everyone will be having the kids in your home and you will be helping your kids in doing these things, right? So what is this? What is this? This is reasoning patterns, right? So first red, yellow, green means obviously the next will be coming under the red, yellow, green boxes. Okay, this is the reasoning patterns. So why why do I learn to draw these patterns? What is the necessity? So everywhere the pattern is there. What is the necessity to learn these patterns? So because patterns have recognizing pattern is a very important skill actually. That's why it has been embedded in the school curriculum itself. Okay, so what is the importance of these patterns? So the learning patterns are the heart of math. The first thing is patterns are the heart of math. Then the ability to recognize and create patterns help us make predictions on our observation. So I'll be observing something. So I am observing some patterns. So from the patterns, I will be predict some output. So it might be like this, as it is following this kind of pattern. So it is the things are evolving like this. So I can come to a predictions based on my observations. For that, the pattern will be helping me. And the next is we use patterns to represent identified regularities and to form generalizations. So say for example, in the previous slide, I can tell that the thing is following like the square, it is following red, blue, green. This is called as generalization. That is identified regularities and to form generalizations. And the next is patterns allow us to see relationships and develop generalizations. Not only the regularities, it is also used to identify the relationship between the objects, right? And develop generalizations. And patterns provide a sense of order in what might otherwise appear chaotic. So for the best example for this is in the next consequent slides, I am telling about the chaotic matter. That is, in you have to recognize the patterns in a sense, that is in a proper way. Otherwise it will end up in the different thing, that is hasty things. So the researchers have found that understanding and being able to identify recurring patterns allow us to make educated guesses, assumptions, and even the hypothesis. So the base for these things is the patterns, and it helps us to develop important skills of critical thinking and logic, obviously. So in order to increase the critical thinking, only these things are embedded in the school curriculum itself. So I think so he is a well-known person. He is none other than Arthur Lee Sample, the inventor of this machine learning in 1959. He coined the term machine learning in 1959 in his article, and he is an American pioneer. And the time he coined the machine learning is for this checkers players program. That time itself, it is a world's first successful self-learning program. It is a self-learning program. Okay, and he is none other than Lawrence Gilman Roberts, and he is called as the father of computer vision. So there is a difference between image processing and computer vision. The image processing, what are all the things we can do or we can manipulate the images, it comes under the image processing. But the computer vision is after I am manipulating the images, I'll be getting some data or information. With that, what are all the useful things I can do, that is called as, with the analysis, what are all the useful things I can do, that is called as computer vision. That is the advanced thing, that is the last stage of the last, even you can tell this is the last step in image processing. Okay, so this is the computer vision, and he is the father of computer vision. So that time he has done the 3D, from 3D he will be collecting the 3D features, and from that he will be delivering the 2D images to the world. That is the it's simply you can call it as a graphics. So is it so? So they are telling, and we, of course we are telling, that machine learning and these things has come around, if I am correct, 1959. Is it so? Can you guess what is this? Any guess?
Biometric pattern.
Biometric pattern. Okay, right. So to my concern, the whatever the technologies, right from AI, right from machine learning, and what to tell, right from genomics, astrophysics, astronauts, that is as dealing with the astrophysics, whatever the technology, even the agriculture, whatever the technology we are handling now, it is not developed in past two, that is 10 to 30 decades or even the 50 decades, but it has been brought from our ancient era. Ancient era is the beautiful ethnic Mahabharata. It is a very good encyclopedia. We can call it as an encyclopedia of the technologies. All the technologies has been embedded in Mahabharata. So, for example, if you are taking the genomics, that is genetics, the best final product of the genetic algorithm is Bishmer. You know, you have come across the Bishmer, right? So he is having the slow aging and long living product. We will call as a product, right? So he is called as the son of Ganga, right? So the technology behind this is the bacteriophages, which is available in the Ganges River, is responsible for slow oxidation and slow cell decay. That is reduced oxidation and cell decay is the characteristics of that bacteriophages. So he might be called as the son of river Ganga, right? So that is the best final product in the genetic algorithm. Likewise, in astrophysics, if you are taking the astronauts, so Sauba Vimana and many other things, you can even the ancient robot is nothing but barbaric is an ancient robot, and he is doing the things, he cannot think of his own. He is, everything is rule based for him, and all those things. So you can tell any number of things for this technologies, whatever we are using. So it is not leaving the patterns also. So that's why I am telling all those things. This pattern is nothing but chakra view. I think so. Now you can see this. This is the invincible chakra vyuha. This is the ultimate thing they have done in the Kurukshetra. That is Dronar formed this, and he had killed that Abhimanyu. Yeah. So I have told in the previous slide that learning patterns is not important. You have to learn the patterns in the order, that is in the sense. Then only it will be good, otherwise it will be hasty. The best example is this one. Abhimanyu know how to enter into the Chakravyuha, but he doesn't know how to come out of the Chakravyuha. Because of that, he got stuck up in that and he lost his life. Right? So this Chakravyuha itself is a very good pattern. Still, the military in defense, this is the actually the what we get the advanced war method. This is the advanced war method that has been incorporated in the Mahabharata era itself. This is called as Chakravyuha. In Chakravyuha, we can identify the pattern like it is having some 7 layers. That is the first thing. And where to place the different, that is, say for example, archers, that is those who are well versed in bow and arrows, archers where to place, and infantry where to place, and those who are well versed in sword where to place. So these will be predefined, and everyone, it is like a spinning wheel. So the soldiers will move in the opposite direction, and it is seems like a discus, no, discus, we'll be throwing the discus disc, no? So it will be like that, and it cannot be identified from the ground, and we can identify the chakra vyuha only from the top. So the thing is, based on the music, they will be playing the music like drums, and based on the music, the soldiers will be moving. So this is the pattern. Actually, this is the pattern in the chakra vyuha, right? So what are all some related disciplines? It is not limited to. It is some related disciplines that depends upon these patterns. It is none other than image processing, obviously, computer graphics, pattern recognition, and robotics and AI. This pattern recognition is following have been incorporated in all the four. That is image processing, graphics, robotics, and AI. If I am talking about AI, it is a ocean. AI means machine learning. If I am going for machine learning, I have to talk about the deep learning also. Everything is interconnected, and that is the subset of the deep learning subset of ML, and ML is the subset of AI. So coming to image processing, it is very simple. The 2D image, what the 2D image I am feeding, I will be getting back the same 2D image only in case of image processing. Okay, all you people all know what is image, what is images, what is graphics, and what is the computer vision. So I am going to tell only the difference of these three things. I am not going in depth in everything. Okay, so this is the 2D image. I'll be performing some operations on those 2D images. Say, for example, I'll be doing the pre-processing and segmentation and object detection kind of things. Yeah, of course, the enhancement also. So after that, I'll be getting the same image. That is same image in the 2D only. Okay, this is the image processing. So say, for example, I am taking the X-ray image. So first thing is I have to remove the noises. That is the reduced noise. Increase the visibility of the images. The detail is in blur. After I am applying the image enhancement techniques, so I will be getting the details of the image. It will be, the blur will be removed. And we can do this with the help of the contrast adjustment. That is contrast enhancement techniques. That is adjust and optimizing the contrast. So coming to the next, computer graphics. In this, I am taking the 3D geometric data, but I am producing the output as 2D image. 3D geometric data will be taken, and I am applying the algorithms, and I am getting the 2D image as the output. So compute light interaction and geometric projection from 3D to 2D. This is computer graphics. So like this, I will be getting the coordinates, and I am projecting the 3D, right, in a 2D, two-dimensional space. That is the computer graphics. And in computer vision, I'll be getting the 2D image. Okay, and from that, in this might be the ulta of the computer graphics. That is, construct the 3D geometric data from the input. So the output will be 3D geometric data. Say, for example, this is the computer vision. So I am taking the 2D image, and I am doing the operations, and I'll be getting the 3D geometric data. Okay, so now comes this pattern recognition. What is pattern recognition? Obviously, it is analyzing the pattern, otherwise analyzing any object or any images to our concern. So recognizing the patterns is the process of recognizing patterns by using machine learning algorithm. So pattern recognition can be defined as the classification of data based on knowledge already gained. So in machine learning, the machine will be, what is machine learning actually? I don't know about the participants, whether they are very well versed about these terms, machine learning, AI, deep learning kind of thing.
Yes, ma'am.
Okay, so it's very good then. So machine learning is nothing but we are going to give some artificial intelligence to the machine to learn whatever it is respect to the application, to learn the things from its surroundings or the data. Okay, so based on, so the pattern recognition can be defined as the classification of data based on knowledge already gained or on statistical information extracted from patterns. So otherwise, the two choices, one, it will be fed with the knowledge already. Otherwise, from the patterns, it will be extracting the features and informations, and based on that, it will be making the decisions. Otherwise, it will give some representation of what it is fetching. Okay, so the first kind of thing is nothing but your machine learning, and the second kind of thing is nothing but your deep learning. That is the actual thing. In a typical pattern recognition application, the raw data is processed and converted into a form that is amenable for a machine to use. Right? So before entering into any machine learning algorithm, the primemost thing you have to do this pattern recognition. Unless and until if you do not process the raw data, the machine cannot, suppose I am feeding my image as such, it will not be useful for the machine to learn. So instead, if I am feeding the features of my image to the machine, it will be learning something from the features. Right, so the data is processed and converted into a form that is amenable for a machine to use. This is the pattern recognition, involves classification and cluster of patterns. Both the classification is, of course, it is a supervised learning, and clustering is the unsupervised learning. So it involves both classification and clustering of patterns. So in classification, an appropriate class label is assigned to pattern. As I said earlier, it is a supervised learning, and clustering is the unsupervised learning. So in classification, I will be giving all the labeled data, and I will be asking the machine to learn from the labels. That is nothing but your classification. That is, suppose we are learning to drive the cycle. Otherwise, we are learning the letters in our childhood, A, B, C, D. How we learn? We are learning with the help of the teacher. So he is telling this is the, if it is having 3 lines like this is A. So this is nothing but the classification algorithms. All the classification algorithms comes under the supervised learning. One supervisor or otherwise a teacher will be there for this to train the machine. But in clustering, I'll give all the things, and from that I have to identify what are all the similar things. Say for example, I will be giving you the mixture of colors, and you don't know what the color names and all. Obviously, what you will do, you will be segregating the same colors. Say for example, these are seen in a similar color, red, green, and blue, something like that. But you don't know this is red, this is green, and this is blue. You will be clustering the things, and you will name yourself. That is nothing but your clustering. Okay, so the labels will not be there. So for that, there is no need of a teacher or a intermediate to train the machine. That is the clustering algorithm. And of course, I said you about the features and feature vectors, which is the primemost thing for the patterns. Unless and until we do not extract the correct features. So why? Because if I am feeding an image, it will be having some minimum of 100 to 200 features in a particular single image. But all the features is not necessary for the machine to identify the things. So the proper features has to be extracted. So many feature extraction algorithms are there. Say for example, histogram of gradient is actually the benchmark algorithm for the feature extraction. So using those things, we'll be extracting the right features, and we will be forming the feature vectors with those features, and we'll be giving those things to the machines to learn. Okay, so the features may be represented as continuous or discrete binary variables, and it is a function of one or more measurements computed so that it quantifies some significant characteristics of the object. So for example, I am recognizing the disease in the leaf. Otherwise, I am recognizing some diseases in organs. Means the particular differentiation, that is the level of intensity where where it is changes in the images, that edges alone is the major features, not all the pixels. Okay, so it quantifies some significant characteristics of the object, that is called as features. For example, in our face, we will be in face recognition, we will be putting the points, important points, that is recognizing the face. Say for example, eyes, ears, nose, and mouth. Okay, so these are called the features. Obviously, manually also we will be observing a human with the help of these features alone, eyes, nose, and mouth alone, so not by the colors, right? So a set of features that are taken together forms the feature vector. As I already said, we'll be extracting the features and we'll be forming the feature vectors. So example, in the above example of face, if all the features taken together, then the sequence is feature vector, and the feature vector is the sequence of features represented as d-dimensional column vector. Okay. So these are all the some of the important features of the pattern recognition. So pattern recognition systems should recognize familiar pattern quickly and accurate, right? So when I am going for the pattern recognition algorithms, otherwise I am going to build a pattern recognition system, it should be accurate, and as well as it should be fast enough to do the things. Okay, say for example, in medical imaging, all the will be, if you are building a pattern recognition system, obviously initially we will be getting the accuracy of 80 or even 90 is the best, 90 or 92 something. But in medical society, they will not be accepting the accuracy of 90 or so. Even if you are giving the accuracy of 98 point or 99, they will be checking of their own all those things, right? So the accuracy is the prime concern, and recognize and classify unfamiliar objects, that is the outliers. Okay, and we'll be if we recognize the patterns correctly, actually what we are doing is we are throwing out the outliers. We are taking only the patterns and we are throwing out the outliers, which are waste, actually the waste informations. And accurately recognize shapes and objects from different angles and identify patterns and objects even when partly hidden. So recognize patterns quickly with ease and with automaticity. So these are all the some of the features, and the objective is, obviously we are working, all the researchers will be concentrating on these things only, that is minimizing the average error, minimizing the risk, that is the wrong decision could be more risky in some cases, such as medical diagnosis. I have stated this already. Why I have to automate this? Obvious reason, save from time and effort. Say for example, if actually we are in Silchar, I am working in NIT Silchar, obviously you know, people know this. Silchar is a town, so this is like a hill area, and the um, uh, resource here, the resource scarcity is everywhere. Say for example, we are having the Kachar Cancer Hospital here, and I think so you have come across these things, the Padma Shri Dr. Ravikannan. Actually, he is from our Adayar Cancer Institute, professor from there, and he resigned his job and he is doing service here in Kachar Cancer Hospital right from 2007. And now he got Padma Shri because for his service. And here, there, actually it is a trust hospital. Kachar Cancer Hospital is a trust hospital. There the facility is very poor, and the resource persons also, there is a shortage of resource persons. Say for example, pathologists. The pathology is the one prime thing who identifies the cancers, right? So we can, if we try to automate the things for them using our AI, it will reduce the workload of the pathologist so that she can do the things faster. Okay, so the time will be saved, and resources will be saved. So because of these things only, we are going for the automation. And how do machines solve it is based on these algorithms. I'll be discussing some well-known algorithms in the last, that is the template matching, or otherwise based on the statistics, that is mean, median, mode measures are there in statistics. So based on those statistics, we can uh, recognize the patterns. And neural networks, this is the heart of the machine learning, that is artificially we are thinking, our thinking is based upon our neurons in the brain. Likewise, we have to build the neurons for the machines, that is the artificial neural network. So tree classifiers support vector machines for classifying the yes or no type of kind of thing. That is the whether cancer is there or not kind of thing. We are going for this SVM support vector machines and multi-classifiers. Multi-classifiers in the sense, if you are going for the by in the sense yes or no type, we will be using the SVM is the benchmark, and the multi-classifier is multi-class SVM is there, that is grouping some more than 2 classes. Say for example, what kind of disease it might be. So it is whether it is healthy, if it is disease, what kind of disease. So you will be having some other labels like it may be a cancer, lung cancer, or maybe a blood cancer, all those things, right? So these are the multi-class SVM. And what makes these to happen? Now only it is booming. The AI is booming like anything. We are talking everywhere. We are talking about deep learning, all those things, right? How this comes into that too, for the past 10-20 decades, the AI is booming like anything. Why and how these could happen? Can any guess this movie? It is the movie. One is, if I am correct, Irumbu Kudirai, and other one is the boys.
இந்த விவரம் தான் என் மூலதனம். நான் உனக்கு தர்றது சோறு இல்ல தம்பி, இம்ப்ரமேஷன். இம்ப்ரமேஷன் இஸ் வெல்த்.
ஏதாவது சாதிச்சே ஆகணும். அப்டேட் யுவர் செல்ஃப். இன்ஃபர்மேஷன் இஸ் வெல்த். குட் லக். ஜெய் ஹிந்த்.
Right? So this is the reason. Actually, daily we are getting, especially in the healthcare systems, we are getting tons and tons of gigabytes of data. We are getting in our cloud, or knowingly or unknowingly, we are also generating the data. We are putting our photos in the Facebook and we are sharing so many things. So unknowingly or knowingly, we are generating tons and tons of data. What to do with this data? We have to extract some information from this. On those days, the information is not, the internet connectivity is not like as like now. So the sharing of the data will not be there. So obviously there will be scarce of data. So that time it is not possible. But now we are having tons of data. That is, the big data is available in all the fields. So from that, we have to extract the information, right? So this is the thing behind why the AI is booming now, right? So what is the learning? Learning is nothing but learning is the experience. So I learned to I'm learning the bicycle from someone. Otherwise I'll be learning like walking, I should be balancing like this. All those things, it is by experience only. So if, say for example, even this talk, I am by experience only. If I am doing this for a long time, I will be expert in all those things, right? Likewise, if you have more experience, you will be learning more things, right? Otherwise, so say for example, this is for the case of human learn from the experience, but we cannot give the experience to the machine, but simply we can give the data to the machine. So as I said earlier, we are having tons of data. So we are going to give the data to the machine, and the machine will learn from the data. So the experience is equivalent to now here data here. So if you have more experience, you will be learning more things. Likewise, if you have more data, the machine can learn easily and it will produce some accurate results what you are expecting, right? So the data is the important thing. So training and testing the pattern recognition. So learning is a phenomenon through which a system gets trained and becomes adaptable to give result in an accurate manner. So learning is the most important phase as how well the system performs on the data provided to the system, on which algorithms used on the data. The entire data set is divided into two. One is for training. So say for example, in schools, we are learning, right? We have learned from our schools. We have learned the subjects. Still we are learning. So simply learning itself is not enough. So we are, so say for example, the teacher will be teaching our kids the letters A, B, C, D, otherwise any subjects. So that is called as training. So after training, they will be assessing whether they have reached the things what they have taught. So that is called as testing. So only they are keeping the test. the midterm test or something called PT or a half yearly, all those things. This is called as testing. So the training is the important part as well as the testing too. To validate the system, we need this testing. So the testing could be done with the help of data only. Say for example, from anywhere from you will be learning the entire lesson, and anywhere from the book, from the lesson, they will be asking the question. So that is also from the same data only, right? So we'll be dividing it in the ratio of 70-30 or 80-20. And 80 will be used for the training and 20% of data will be keeping for the testing to validate the system. This is the training set. It is used to build a model. It consists of set of images which are used to train the system. Training rules and algorithms will be there. That is the main thing for extracting the patterns. Used given relevant information, how to associate the input data with the output decision. So the system is trained by applying these algorithms on the data set. All the relevant information is extracted from the data and results are applied. And I already told you the thing is usually we will be having the 80% for the training and 20% for the testing. So I have mentioned here the 20% of data set is used for testing. Say for example, a system which identifies which category a particular flower belongs to is able to identify 7 category of flowers correctly out of 10, and rest of this are wrong. Then the accuracy is 70, obviously. Okay, this is how we'll be testing. So I have trained the machine to classify 10. Okay, so but it is classifying only 7 flowers correctly, and remaining 3 it is not classifying correctly. It is giving some mismatch errors. Then the accuracy will be obviously 70%. So what is the merits and demerits of PR? The advantages, obviously, pattern recognition solves classification problems, and the pattern recognition solves the problem of fake biometric detection. Not only fake biometric detection in visually impaired blind people, speaker diarization, even in NLP now, the NLP in par with the image processing, the natural language processing is also booming now. In that they are text to text translation, image to text translation, text to image translation, all those things they are doing wonderfully. And likewise, the major part, apart from this artificial neural network, convolutional neural network, that GANs, that is generative adversarial neural network, is the one thing which is doing miracles in the deep learning networks, right? I'll be telling those things later. And the disadvantage is, this is the main disadvantage. Sometimes to get better accuracy, larger data set is required. Still, we are suffering for the data set. Say, for example, I am doing the research in medical imaging in diverse areas, one in medical imaging and other in video surveillance, and in agriculture sector too. In video surveillance, say, for example, we are doing the research on traffic sign detection for the Indian roads. That is, that traffic sign is not normal traffic sign, it is a cautionary traffic sign. Cautionary traffic signs in the sense, you will be say for example, unmanned vehicle, that is unmanned railway gates will be there, so there will not be any gates. So in the villages still it is there will not be any gates, so they will be keeping the board there. It is what to tell, unmanned railway track is there. So if we don't know about those things, we will be simply crossing the railway track, and many accidents we can still it is happening, right? So likewise, the school zones, speed breakers, kind of things we are trying to identify, but there is no data set for the Indian road itself. That is the biggest problem. What are all the data sets available in the open source? We are this is for their countries like German. Okay, so that will not be suitable for our Indian roads. So we are generating the data sets of our own for the research works. And agriculture also, we cannot rely on the satellite imagery. So this is the one problem in the pattern recognition. So for better accuracy, we need the data set. The data set minimum of 5,000, 10,000 images. Then only the accuracy will be high. This is the main demerit. And the syntactic pattern recognition, it is very complex to implement. That is the another structural pattern recognition, syntactic pattern recognition. Two things are there. I don't want to go in depth with it. So syntactic pattern recognition is very complex, and it is complex to implement. So these are some of the applications. There's the image processing, segmentation analysis. Obviously, you know, computer vision, I have told you already. Seismic analysis is the earthquake kind of thing. So predicting those things. Even the cyclone, we are hit by the cyclone recently, you know, that Tamil Nadu have faced the things. So this is the seismic analysis, climatic changes. That also depends upon the pattern recognition only. If we are lack of data, proper data sets, that's why we cannot tell exactly whether it will be rainy or today or tomorrow kind of things. But in US, they will be telling that within 10 minutes this place will have a heavy rain, otherwise a moderate rain, so all people are requested to go inside within 10 minutes. They are telling the time even. So because they are having the database like that, they are creating the data sets like that. Okay. And radars, obviously wireless sensor networks, that there also we are following the pattern recognition. It is in from easy, and speech recognition, fingerprint, that is a biometric. Okay. So now comes to what is the medical image processing. Okay. There is two parts in my session. I already told you one is pattern recognition and the other one is the medical imaging. So MI focuses on two major tasks. Total medical imaging, we will be, whatever the research we are doing, it will be falls in any of the two categories. One is either we'll be improving the pictorial information for human interpretation. Say for example, enhancement kind of thing, right? Otherwise segmentation kind of thing. So that is the improvement of pictorial information for human interpretation. That is the doctors, for the doctors. And the otherwise what we will be doing is processing of image data for storage, transmission, and representation for autonomous machine perception. That is the second category. So that is automated kind of thing. Okay. So this is the two focuses on medical imaging. So easily we can tell that some argument about where image processing ends and fields such as image analysis and computer vision start. This is the medical image processing, with which simply the image processing is alone is not sufficient for medical image processing, right? That the image processing ends and the fields such as we are going beyond that, that is the image analysis and computer vision. What we can, first we will analyze the images, the processed image, and another thing is computer vision. I already told you the computer vision is the after analysis, what we can do with that, how it can be represented in an efficient way for proper diagnosis. That is the computer vision. So this is the medical image processing. And it is with the development of problem-specified approaches to enhancement of raw medical data for the purpose of selective visualization as well as for further analysis. And medical image analysis is different. This concentrates on the development of techniques, it is the supplement the mostly qualitative and frequently subjective assessment of medical images. Qualitative and frequently subjective assessment. Say for example, CT images I am taking for brain means it is for brain, it is for lungs, it is the subjective assessment. Likewise, for based on diagnosis, based on diseases also we can go for the analysis. Say for example, cancer or for diabetic, like so based on diseases also we can go for the analysis, and provides a variety of new information that is quantitative, objective, and reproducible. And special nature of medical images is it is derived from method of acquisition. Say for example, CT images, it will be having a similar pattern, that is white and gray matters will be there, and in MRI also it will be there, but it will be ulta, that is the soft tissues we cannot see in the CT, and in MRI we can see the soft tissues as gray matters. There in CT you will be seeing it as white, black matters, that is the white opaque will be there. Okay, so this is the method of acquisition, and the subject whose images are being acquired, and ability to provide information about volume beneath the surface, not only the surface 2D, from the 2D, now we are implementing the algorithms to generate the 3D view of those things. So those surface imaging is used in some applications. So image obtained for medical purposes almost exclusive probe the otherwise invisible anatomy below the skin. And information may be from 2D projection or 2D slices. 2D projection is X-ray. For 2D slices, we are going for CT, and full 3D mapping, we are going for this MRI, PET, and 3D ultrasound. That is, all the medical images will be having its unique characteristics. So these are some of the advantages of medical images, that is dealing with medical images, the knowledge of what is and what is not normal human anatomy. That is, say for example, if you are taking the X-ray of, even suppose I am having some pain in my hands, so I am taking the X-ray, then I could identify that I am having a fracture here. So this is abnormal, right? Suppose if everything is okay, this is because of some muscle pain. It is normal. That is, so what is normal and what is not normal in human anatomy. And selective enhancement of specific organs or objects by using some injection of contrast enhancing material. So we have come across the CT scanners and MRI scanners, and in those things we are having CT contrast as well as MRI contrast. So they will be injecting the radioactive materials that will be absorbed by the organs, and we'll be tracing that and we'll be getting the images. So that is the selective enhancement of specific organs. All these differences affect the way in which images are processed and analyzed. So validation of medical image processing and analysis techniques is also a major part of a medical application. That is actually not a major part, that is the prime part. Okay, validation is the very important. So we'll be having so many evaluation metrics for our algorithm. Say for example, right from F1 score, precision, recall, so PSNR, MSE, so many things we'll be doing for our algorithm, and we'll be proving that I am giving the best result of segmentation of the cancer. It is a 99%, but it can be cross-verified by the biological evaluation by some other pathologists or doctors. That is the, if that has been done, then it will be the added advantage for your algorithm for the justification of your work. Okay, so the validating result is always important. The scarcity of accurate and reliable independent standards create another challenge for medical imaging. So the medical imaging systems, that is the radiology, mammography, angiography. So these are all the major partitions we can tell in the medical imaging system. Imaging systems in the sense how the medical images are captured, with what type of scanners they are using. That is called as medical imaging systems, or otherwise imaging modalities, what modality they are using for capturing the images. Okay, so these are all the different imaging modalities. One is the computed tomography, MRI, digital subtraction, angiography. Subtraction is nothing but converting the white into black, black into white. That is the inverse. So this is the digital subtraction for angiography, and Doppler ultrasound imaging. Other techniques like PET, SPECT are there. So this provide a valuable addition to radiologist imaging tools towards more reliable detection and diagnosis of diseases. So in all medical imaging systems, say for right from CT or X-ray or a MRI or a PET, SPECT, whatever it may be, we can ask these three questions. The one is, what does the image show? Or any imaging modality, and how good is it? The next one is, how is it made? So these are all the three questions we can ask for any imaging modalities. So first comes to this X-ray image. Okay, so what is this? This is nothing but an X-ray of hand. Two X-ray views of the same hand are formed on a single film by exposing the hand onto half of the film, while the other half is blocked by the first will be blocking one half and the hand will be projected. Next will be the next half will be blocking and another position of the angle will be projected on the same film. Okay, so this is the X-ray views, that is two X-ray views of single hand. This is the image. So what is good in it? So yeah, the fracture of middle finger is seen on the both the views, though it is clearer in the view of on the left. In the left, it is seen clearly, but still we will not be relying. Obviously, in medical history, they will not rely on a single image. They will be taking multiple X-rays or multiple CT scans or MRI, all those things to confirm the things. Though it is clearer, the view on the left, the image can be used for the diagnosis to distinguish between sprain and fracture and to choose course of treatment. So these are all the good things in this X-ray image. So how the X-ray is actually working, that you have to know. So obviously it is a electromagnetic radiation. It principle behind this is electromagnetic radiation, and it is invented in 1895, if I'm correct. An X-ray is produced when a very that is a negatively charged electrode is heated by electricity, and those electrons are released and thereby producing the energy. So this is the concept behind this X-ray. That energy is directed towards a metal plate or anode. That is, the thing is released from the cathode, so it obviously it will be moving towards the anode at high velocity, and an X-ray is produced when the energy collides with the atom. That is the metal plate. Okay, so we know these things already. That is, the X-ray is for bones. So if you want anything to see in the bones, we will be using for the X-rays. Why? Because this is opaque. The bone will be opaque, so it is again transmitting the things there. Okay, so and another thing we know is X-ray is we are exposed to radiation. So there is the disadvantage of this X-ray mode is there is more chance for the radiation cancers. Okay, so this is the X-ray imaging. How it works is this is how. So the image will be captured by in the film. Okay, so oldest non-invasive imaging of internal structures, rapid short exposure time, and it is inexpensive. Obviously, it is the cost effective. Even for 100 to 200 rupees, we can able to take the X-rays. But if you are going for the CT scan, minimum of 3,000 to 4,000 is needed. And for MRI, it depends upon the hospital, from 8,000 to 14,000, they are demanding for the MRI and the MRI contrast, right? And this is unable to distinguish between, but here we cannot identify the soft tissues, right? Okay, so we can identify the problems in the bone, and the real-time X-ray imaging is possible and used during interventional procedures. And ionization, I said already, ionizing radiation is there. So the radiation cancer is the major risk in case of the X-rays. So if you want to analyze any bone kind of thing, say for example, even now for COVID, we are using the CT, chest CT, right? Before chest CT, actually the lungs will be analyzed with the help of the X-rays only. For even for cold, how much cold is we are having in our lungs, for that we'll be going for the X-rays. Okay, based on the shadows, they will be telling we should be specific. Say for example, if I am handling the lungs part, then either chest CT or lungs X-ray of lungs is needed. Okay, suppose I am going to work on brain, so MRI is the best option for the brain as well as for the spine too. So this is CT, this is computed tomography. This is the CT image of plain through liver and stomach, projection image from CT scans. So what is it? It is nothing but the image of section through upper abdomen of patient prior to abdominal surgery. And that is the previous images. What I am discussing is about the previous images. The section shows ribs, vertebra, aorta, liver, and partially filled with the liquid. What is good in it? The set of CT images from the heart down to coccyx was used in planning surgery for alleviation of intestinal blockage. For that, they are using this chest CT, and the surgery was successful. So before I'm going to this, I think so the audio, you can hear the audio, right?
Yes, ma'am.
Okay.
Yes, ma'am.
Yes. This is 1 minute video only.
A CT scan is an X-ray procedure that creates cross-sectional images with the help of computer processing.
Actually, it is X-ray only.
CT images are more detailed than conventional X-ray images and can reveal bones as well as soft tissue and organs. A conventional X-ray uses a fixed tube that sends X-rays in only one direction, while a CT scanner uses a motorized X-ray source that shoots narrow beams of X-rays as it rotates around the patient.
It is not a straight in one direction.
There are special digital X-ray detectors located directly opposite the X-ray source. As the X-ray passes through the patient, they are picked up by the detectors and transmitted to a computer. Image slices can either be displayed individually in two-dimensional form or stacked together to generate a three-dimensional image that can reveal abnormal structures or help the physician plan and monitor treatments.
Okay, so this is the concept behind this. It is like fan beam projection. They will be calling it as a fan beam computed tomography. So in normal X-ray, it will be in a straight direction. There is a unidirection, and here it will be going around, and it will be working on slices. It will be slicing, and the images will be captured like that. Okay, so because of this, you can even get the soft tissue images, but in X-rays you cannot get the images of soft tissues. But here in CT, you can get the images of soft tissue even. Okay, so this is also working. The concept behind this is it depends purely upon the X-ray only. So as I am telling about, it is working on X-ray. The same whatever the effects which we are facing in the X-ray, that is the radiation cancer. The ionizing problem is here also. We can that is in CT images also. That's why we are asked to, if someone is accommodating the patients, they will be asked to put the code, that is the ionization, that prevents it from the ionization in CT as well as in the X-ray also. So as I said earlier, the another major thing is, suppose if we have any metal implants like what to tell, in heart we will be having the pacemakers, right? So that is the metal implant. So if the patient is having the metal implants, then exposing them to the CT or the X-rays, it will harm them. Actually, it will, as the metals are inside our body, we should not be exposed to the X-rays or CT scanners, right? So the images of sectional planes, it is giving the images of sectional planes while revolving around our body. It will be giving the images of sectional planes. The sensors will be there that will transmit the signals to the computers, and the images will be generated. And CT can visualize small density differences, gray matter, white matter, and CSF. CSF is the what to tell, that is the liquids, that is the liquid part from cerebral brain to abdomen. Till you are having the spinal fluid, you will be having the cerebral spinal fluid. So that also we can see in the CT. CT can detect and diagnose diseases that cannot be seen with the X-ray. More expensive than X-ray, but lower resolution. Here also we are having the ionizing radiations. So then this is the functional MRI. There are two types of MRI. One is the structural MRI, and if it is undefined, that is, you are not specifically telling it's a functional MRI. Simple MRI is the structural only. That is, the MRI will give the structural and anatomy of any organs, but it is specific to brain and spine. Okay. If I am specifying the MRI as functional MRI, Then I'm going for the MRI contrast. MRI contrast is you will be injecting the dye. The MRI you will be using the dye called in CT you will be using the dye iodine dye, but here the iodine dye is not used. So it is not in CT contrast. You will be using the iodine dye. That iodine dye is allergic to many of the patients, but in MRI imaging you are not using the iodine dye. Some other reactive materials you will be using for the as a agent. So with that you will be identifying the function of that organ also. Normal MRI you will not be identifying the function. You will be identifying the structural and anatomy of the organ only. Okay, so this is the functional magnetic resonance imaging. And here you will be having fixed 1 to 16 slices, same like CT, but the principle is entirely different. In MRI it is having two words, one is magnetic, another one is resonance. So you will be having, instead of x-rays, the same machine will be like a duffnet thing only. That is, you will be having a ring like thing and the patient will be inserted there. That thing will be having so many magnets, so it will be producing the magnetic fields. Our body is say for example 70% of our body is filled with water, right? Other than the proteins, all those things, so it is filled with water. The water is having the hydrogen molecule nucleus, so in that the protons will be there. So based on, so if the strong magnetic field is interacted with this protons, it will be aligning in the equilibrium. And once the radio frequency is applied in the reverse, so it will not come to its original position. It will be deviating to the next extent. Once the radio frequency is getting off, that is the electricity is getting off, so it will slowly come to its original normal position. So the MRI will be getting the images by studying how it is coming to the normal position. Otherwise some protons it will not align in the normal itself. So based on this they will be analyzing the anomalies. Okay, so this is the MRI principle. Here there is no ionization, no X-ray, all kind of things. Only magnetic field is applied and electricity is applied. Okay, so this is the functional MRI. So 2 of 16 planes, 2 of 16, not only one, 2 of 16 planes through brain of subject participating in an image naming experiment. So images are superposition of anatomical scans, that is the gray, and functional scans, it is colored. So here you can see both the things. Color is the functional and simply gray, it is the structural. Okay. Plane 3 shows functional activity in, so each in brain, if we are slicing the brain into different sections, so each section will be having specific organs functionality. Say for example, for visual cortex we are going for the plane 3, and plane 6 we are going, shows the activity in speech area. Okay, visual cortex is nothing but vision. Okay, so what is good in it? This set of images is part of research on brain function, and the functional imaging is used prior to brain surgery to identify structures such as motor areas that should be avoided and focal areas for epilepsy. And that is what they are telling is motor area is, we are having 5 sense organs, that is called as the motor areas. We should not touch that part. So such as motor areas that should be avoided, and focal areas for epilepsy. Where epilepsy will be there, that is the tumor will be there, we have to concentrate only on the focus. The focus is on the epilepsy only. Okay, so for that we are going for this functional MRI. And also the functional MRI may be used, that is contrast MRI may be used whether to identify your tumor is the benign tumor or it is a malignant tumor. That is whether the tumor is active or it is a simply passive tumor. Okay, so for that also we are going for this functional MRI. This is the features. Obviously it is a no ionizing radiation is there, and many contrast mechanisms are there. Contrast between tissues is determined by pulse sequences, and it can produce sectional as well as projection of images. Slower, obviously it is slower, and it is more expensive than X-rays, right? Likewise, we have to bear the noise while we are while the machine is running. It will be producing different kinds of noises to high extent. So our ears will be closed if we are undergoing the MRI scan. And this is how it is working.
An MRI scan looks deep inside your body to produce detailed images. But how does it work? MRI, or magnetic resonance imaging, uses magnets, really strong ones. Magnetic fields are measured in Teslas, and a typical MRI scanner produces 1.5 Teslas, more than enough to pick up your average car. But it also has an interesting effect on the particles in your body.
MRI scanners.
The human body is made up of all sorts of things, including fat, protein, and other stuff like minerals. But most of it, around 70%, is water. These water molecules sit around in nearly all parts of your body, and under normal conditions, they float around happy and carefree. The atomic structure of water includes 2 hydrogen atoms and 1 oxygen atom,
This I
hence
have
the
explained
H2O.
earlier, the
And it's the
principle behind
hydrogen
this.
nuclei or protons that are important. Just like the Earth, each proton spins on an axis, giving it what's called a magnetic moment, basically a north and south pole. This makes every water molecule in your body a tiny magnet, and there are billions and billions of them.
So protons.
When exposed to a large magnetic field, the molecules line up and spin at a particular frequency.
Yes.
A secondary magnetic field turns the molecules to face new directions, and when it's switched off, the molecules begin to realign. As
So
they
they
do,
will be
the
studying
frequency
this
changes,
realignment
and that's what allows the MRI scanner
and
to peek inside
they
your
are
body.
capturing the images. Right.
Detector coils placed over your body.
So this is the magnet resonance summary. That is I already told. So this is the ultrasound imaging. You have come across this. So it is mainly for detecting the abnormalities in the fetus, that is pregnancy period. Okay. What is it? It is I already told you. Ultrasound image of woman's abdomen. Image shows a section through the uterus, and it is also showing 2 embryos. A and B are the 2 embryos. It is twins. So 2 embryos in their amniotic sacs can be seen. What is good in it? This image allows a safe means for early identification of twin pregnancy, and obstetric ultrasonography can be used to monitor high-risk pregnancies, and prenatal scans are part of baby picture albums. And a picture is so I'll be directly going to the working of this. I think so I am running out of the time otherwise.
The heart of most ultrasound systems is a device called a transducer,
This is
which
the
uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type
Our
of crystal
organs
can
will
also work in
bounce back
reverse.
these ultrasounds
It can produce
and they
electrical
will be
signals
captured.
when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
So this is the working of the ultrasound images. In ultrasound, that is the sonography, you will be having a probe, and the high frequency sound waves are transmitted from probe to the body via a conducting gel. The gel will be applied, and the conducting gel will be transmitting the high frequency sound to the body, right? So those waves then bounce back when they hit the different structures within the body, and that is used to create the image for the diagnosis. So one advanced thing in this is the Doppler. So in Doppler ultrasound, it allows the Same principle, the ultrasound what we are having, the same principle only will be followed in the Doppler also. In Doppler, it allows the blood flow through arteries and veins to see. We can monitor the blood flow in the Doppler ultrasound. Okay, so this is the ultrasound imaging overview and the moving the structures and flow. That is, if you are want to see the flow and structures, that can be done with the help of this Doppler. And the imaging is in real time, used for interventional procedures. Ultrasound has no known harmful effects. That's why we are recommending these things. The doctors are recommending these things for the pregnancy women and for the fetal observations. Ultrasound equipment is inexpensive, and many anatomical regions, for example, head, cannot be visualized with ultrasound. That is the only drawback. We cannot visualize the brain kind of thing. Even spine also, we can, to some extent, we can find the abnormalities, but many a time the ultrasound image will be missing the abnormalities in the spine also. Okay, so working of Doppler, I think so I can skip now. Single photon computer tomography, there is the SPECT, right? The working of SPECT is something like this. This is the SPECT. You will be injecting it is working on the principle of the radionuclide. You will be injecting a radio tracer in our body, and it will be spread to the entire organs. Based on the emissions, that is, you will be exposed to both X-ray as well as the CT also, and we will be combining, fusing these things, and you will be giving the report. That is called as the SPECT. And here, three-sectional. One is the tomographic images of living heart. Colored areas are measures of metabolic activity of left ventricle muscle. Areas damaged by the infarct appear dark. This seems to be a normal heart. And what is good in it is used for staging. That is, choose treatment before or after a heart attack, and monitoring the effectiveness of the treatment. And you will be having 3 gamma cameras in SPECT. In PET, only one will be there, and in SPECT, you will be having 3 angles of gamma camera will be there. And it will be emitting the radiations into the body, and the body will be responding to those things back. But this is also involves the radiations. Single photon emission computed tomography. This is the computed tomography, and show here is a 3-headed tomography system. The cameras rotate around the patient. A 3-dimensional volume is imaged. In CT, in SPECT, you can get the entire 3-dimensional functionality. Okay, that is the difference between the MRI and SPECT. In SPECT, you will not be analyzing the structural and anatomical details. You will be analyzing only the functionality. Okay, so this is the radionuclide imaging. The radioactive tracer will be injected, and the normal, not all the reflected, the bounce back, the radiations will be absorbed. Only the normal radiations will be taken into account for the image analysis. Only rays that are normal to the camera surfaces are detected. And the features of this radionuclide imaging is the image is produced from an agent that is designed to monitor a physiological or pathological process. That is like blood flow, perfusion, metabolic activity, tumor, brain receptor concentration. But all these are nothing but the functional things, not a structural or anatomical things, right? This is another one, fluorescence microscopy. That is, a normal biological microscope is different. Fluorescent microscopy is different. This works with the help of the laser light. That is to know the living tissue. That is the cultural. We will be giving for culture, culture test. So for these things, fluorescence microscopy will be used to know the living tissue of the cultural cells. Okay. And optical microscope image of a tissue culture. Image is formed with fluorescent light. 3 agents are used. One is a DNA, cytoskeleton, and lipid membranes. It will be classifying with the 3 colors. One is blue, green, and red. Okay. So this is the video depicting this. I don't know. Ma'am, can I continue till some 10 or 15 minutes more? Hello.
Yes, ma'am.
Okay.
Yes, ma'am.
So this is the fluorescent microscopy. I think so. I can skip this. Otherwise, I'll be not sharing about the AI and these parts. So thoughts on imaging, you are having all the image processing techniques will be having these three things. One is the image, that is the object. Object will be captured as an image and the observer will be there. So these are the three entities in imaging. And creative imaging is imaging procedures that create informations. That is called as creative imaging. Say, for example, functional MRI for the first time allows non-invasive study of the brain. Non-invasive study means we are not touching the brain part. Simply with the help of the MRI, we can study, we can know how the brain is working itself, not simply the anatomy of the brain. The function of the brain can be known from this functional MRI. And Doppler ultrasound for the study of flow, and agents for the study of gene expression in vivo biochemistry. This is a single patient CT as well as MRI scan. I have already told you both will be the ulta. So here the darker things are nothing but your soft bones. Okay. Sorry, soft tissues. Here the soft tissues can be identified easily in the MRI. So why I'm telling these things is, when we are going for some spine surgery, both CT as well as MRI will be taken. Why? Because if along with one modality alone, we cannot come to a conclusion. So we'll be having different modalities of the images of the same patient, and we'll be using for the analysis. But the doctors, they will be seeing separately the CT as well as the MRI, and they will be coming for a conclusion. Instead, we can give some algorithms that can fuse both the MRI and CT of the same patient images, and from that we can identify what the information, useful information we can give to the doctors. So that also we can do. That is the fusion of imaging modalities, also a very good research that we can try. This is the MRI and PET. This is the angiogram. And this is the ultrasound. This is for breast and kidney. This is the functional MRI. And functional MRI will be having at off on kind of thing for how many for first 0 second it is off, and on it will be on 75th second. So if there is any change, so it is working properly. So this is the functional MRI, and this is the Doppler for the flow block identification. We can go for this. Mammograms is known for the breast cancers. If you are going to work on breast cancer area, you have to go for the mammogram images. Here we have done the segmentation. We are finding the lesion part, right? So this is right. So now comes the, so now we know what is patterns. We have to recognize the patterns in what? Medical imaging. So how we can do this is with the help of the image processing techniques. So frequently used image processing techniques are here. Actually the window is blurred and he is cleaning, and now it is clear, right? Likewise, the techniques that can be used to improve the images are contrast stitching, thresholding, logarithmic contrast enhancement, exponential contrast enhancement. So this is the contrast stitching. I'm briefing in a layman's approach. So contrast stitching is nothing but it depends upon, we'll be having the histograms, right? Histograms are nothing but it is the X and Y axis will be there. In X you will be having the gray levels, what are all the gray levels available, and in the Y axis you will be having the number of pixels in a particular gray level. Say for example, I am seeing a histogram of any image. If I am having all the pixels in one area, say for example in the either in the darker side or in the brighter side, then I'll be going for the contrast stitching and I'll make the all the pixels equal. Okay, that is called as contrast stitching, right? So here actually the first is the darker image, so I am using the contrast stitching and I am making it a brighter. Okay, so the next is the thresholding. And special case of clipping, and output becomes binary. In thresholding, that is the 0 and 1 kind of thing we'll be doing. And with the help of this thresholding only, we are having this nuclear medicine image axial slice of heart. That is, if I am keeping the threshold value 118, it is coming like this. If it is a 128, it is coming around like this. And this is 138. So depends upon the value, it will be giving the thing, but always the binary output will be the binary image. Logarithmic contrast, very simple. If you want to brighten the dark images, you go for the logarithmic contrast enhancement. That is, here the original is dark and I am lightening that. Okay. The ulta is logarithmic ulta actually is exponential. In mathematical term itself, log and E are opposite. So likewise, this exponential contrast enhancement, what it will do is actually, I don't know whether you can see the original image or not. It is very light. I want to make the light part into dark. I have to go for the exponential contrast enhancement. Okay. So this is the original thing. And after applying the Laplacian filter, that is the high pass filter, I am getting these things. High pass filter will be giving it will sharpen the images. Low pass filter will smoothen the images. So again, I am fusing these two. I am getting the that is the retina. That is the retinal images actually. And so medicine revolves on pattern recognition, classification, and prediction. Okay. So diagnosis. So recognize and classify patterns in multivariate patient attributes. Therapy is the treatment. So select from available treatment methods based on effectiveness, suitability to patient. And prognosis after the diagnosis, what are all the things we are doing? That is the predict future outcomes based on previous experience and present conditions. So to achieve better outcomes in the medical imaging. This is integrating the information so doctors can make decisions with more confidence and care can be more precise. So what is it? Very simple. AI is a great tool to build the future of together. These are all some of the medical applications where we can concentrate. Each and everything is actually a research area. Screening itself is a research area. We are just like that. We are telling it's a screening. Screening itself is we can produce many screening tools. That is the indigenous tools in the screening area itself, and diagnosis, therapy, prognosis, monitoring, health patient monitoring, biomedical and biological analysis, epidemiological studies. Hospital management is simply the files management, and medical instruction and training. Okay. So these are all some of the benefits of this AI in medical imaging. That is, efficient screening tools reduce demand on costly healthcare resources. Data fusion from multiple sensors it is also possible. It help physicians cope with the information overload. So for optimizing the allocation of hospital resources, that is also another research area, and it gives a better insight into medical survey data. So computer-based training and evaluation is the booming thing. So this we might know about the deep learning. Please listen to this. Ben Clocker.
Medical imaging really makes visible what otherwise would remain hidden, and it has already become a key technology in medicine. With a modern 3D ultrasound, for example, I was able to see my daughter 6 weeks before she was born, and actually I got very well prepared for her mood. But the way doctors look at these images is quite different from how you and I would look at them. Doctors get very long and hard training to become incredibly skilled in seeing critical patterns in these images, to tell the difference between healthy development and disease, and to see whether a treatment works or not. But some diseases are so complex that looking at a single image is not enough to fully understand what's going on. And this is where it gets really tricky. So a brain injury, for instance, might show in one image. But to really understand, to get the full picture of the disease, you need to take multiple images, multiple scans with different techniques, so doctors can make a decision. But there's a problem, because reading those complex images is not only very time-consuming, but it really pushes human abilities to the limit. And patterns of disease can often be so complex and subtle that it's really difficult to get it from the images. Brain tumors, for example, they can appear almost anywhere in the brain with very different sizes and structures and shapes. It's very difficult to understand exactly what's going on. And often it's not enough to make a tumor visible, but we need to measure what's going on. For instance, tumor size. It's very important to make a decision whether you do surgery or other options. But tumor size alone is not enough. We need to understand what's happening inside the tumor. For instance, do active parts become inactive when you give a particular drug? Now, this is really important information that doctors need to make the right decision at the right time. And without that information, there is a real risk that critical patterns of disease go undetected. How do we help doctors and make best use of these images? And putting it all together is really challenging, but this is the challenge that we are taking on in my lab at Imperial College. We ask, what if we could train a machine to help us read those images, to detect patterns that humans find difficult to see? And can we even go beyond this? Often we don't know what we are looking for in those images. What are the patterns that describe a disease? Can we build an intelligent machine that can help us find those patterns? Just a couple of months ago, we have all seen a machine beat yet another human world champion in yet another board game. But what was really exciting about this achievement was that the machine's skills were not acquired by programming, but by learning.
Not by programming, but by learning.
Has learned by playing millions of games to detect patterns of great gameplay. And our machine learns by viewing thousands of medical scans. And one of our first big achievements was being able to train the machine to recognize all major organs with an accuracy of a human expert. Now that's really important because now the machine understands what is visible in the image. So we took this further. We then trained a machine that could search through multiple scans and detect patterns of abnormality. We could highlight suspicious regions that might, for instance, indicate a cancer. And that's important because now we can help doctors to not miss important patterns that otherwise by just human reading might have been missed. Recently, we even went one step further. So we now trained a machine that can detect the most complex patterns of brain lesions and putting them all together to build a 3D map of the brain that would show those lesions with an unprecedented accuracy. Now, these maps are so precise that we can start making the important measurements and give it to the surgeon to support their decision. But going from the lab to clinical practice comes with great challenges, and it's about trust. Doctors, understandably, are very reluctant in taking advice from a machine that behaves like a black box. So understanding how a machine comes to a conclusion can be as important as what it decides. So for us as researchers, that's really important. And we were curious, how does our machine understand what a brain lesion is? So we designed it from the beginning so we could lift the lid and look inside. And what we found was really exciting because that's what we didn't expect. When we looked how our machine did this, the interesting thing to note is that we never gave any advice how to detect a brain lesion, how the brain even looks like. But our machine figured out by itself that the brain consists of different structures like gray matter and white matter. We know that mapping those structures is important, but the machine has figured that out by itself. This is what really convinces me that artificial intelligence has so much to offer in medicine. It will not only help us to routinely find critical patterns in very complex data, it will also help us to learn something new, to reveal insights about the most complex diseases and make the right decision when it really matters. Thank you.
So this is the thing I want to tell you people also. So before, actually we are doing the research, simply we will be taking the data set of x-rays or a lung, chest CT or those things, and we'll be trying to identify the patterns. So we are, so think in the retrospective way. First, you have to make the machine to identify the organs. If the machine knows this is the normal one, then it will be very easy for the machine to find the abnormalities. This is the retrospective way of doing the research. That is the thing they are doing in DeepMind also. They have built the model. I'll be showing that video in the last. So it is self-learning machines. It is nothing but the self-learning algorithms will be there. So he is wondering that even we don't know how the brain will be, but the machine, based on the features, it is identifying this is the gray matter and this is the ventricle and this is the white matter and this is the boundary. All those things, it is having separate layers and it is identified those things. The machine learned it actually. Okay. So as it learns the organs, all the organs first, it is easy for the machine to find the abnormalities easily. Okay. So these are some of the PR techniques that can be used in the medicine. So neural networks, base SVM, tree classifiers, and multi-class SVM. I have discussed all these things earlier itself. So the neural networks is the old approach, but still we are, the name is coming in different versions. That is artificial neural network, then convolutional neural network, then deep convolutional neural network for deep learning machines, right? But anyhow, it is a neural networks only. Okay. So it is used in scientific problems, and this is blah, 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 biological and our neurons, artificial neurons. And classification, optimization, what are the areas we can apply these algorithms is one for classification and other one is for optimization. For optimizing, we can depend on the neural networks for clustering, scheduling, and feature extraction. So it is easy to implement self-learning ability when parallel architectures are used very fast and performance at least as good as other approaches in principle. They provide non-linear discriminants, so solve any kind of PR problems. So simply we are depending upon the artificial neural networks for pattern recognition system in one line. And this is the machine learning versus deep learning. I have told you already. In machine learning, we have to give the features, but in deep learning, it will extract the features of its own from the data. Okay, so that is the difference between the machine learning and deep learning. And these are the frequently used neural networks. AlexNet, now we the booming is the AlexNet, VGNet, and GoogleNet, Inception V3, ResNet 101, ResNet 50, all those things are there. So we can go for any of these things. It is already available in the Python library as well as in the MATLAB also. So what next? So this is actually very beautiful. In a simple lab itself, they are using the machine learning algorithms for these things, for detecting the height of the test tube, for based on why, because nowadays we are giving the in labs, in blood test labs, we are giving the blood samples. They will be having a barcode, and in the barcode they will be feeding the other information like what is the patient name and these or those things, and the image only will be sent there. Okay, so from that they will be identifying those things like the color of the lid size, whether it is broken or not, how much the difference is there. Once it is getting reacted, what are the color differences are there. Based on that, it will be giving the reports. Okay, this is also simply image. With the image analysis only, the blood test lab is now running. So this is how. And not only here, in pharmaceuticals also they are using the pattern recognition like this. This is the life science, assist with research and analytical things. So size of the bacteria and all those things. And last but not least, for you will be using the capsules, no? So here see, the original capsule is with the green and red, but if it is some other thing, it will be finding the abnormality in this also, even for identification of mismatch of counterfeits. So like this, we can have any number of applications. Let's talk about your application. So I'm coming to the conclusion part. So medicine is a fertile and active area for computer vision and research. It is ocean. Okay, so any number of daily, we can find any number of problems in this to work, to contribute our research to the society. And unsupervised learning is the next frontier in AI, and the same algorithms, multiple domains. So we can do the algorithms for a single, say for example, breast cancer. It should be robust enough. I can do it for the next also. That is for a lung cancer or for the stomach, like that. Okay, so that is the same algorithm, multiple domains. Creativity and experience are no longer human temperament. Okay, so let's instead of simply artificial narrow, now we are in artificial super intelligence. Artificial narrow intelligence. Narrow intelligence is human is helping the machine to do the things, and artificial general intelligence is human and machine will be on par with each other, and artificial super intelligence is the machine is overtaking the human, and it is doing all the things of its own. But it will take some 2040 or 2050 to reach that, but at least towards artificial general intelligence will be moving now. And finally, this is the Google DeepMind. That model is learning itself, is for jumping, even in the terrain surface. It is a self-learning model actually. This is the concept behind for the self-learning things, self-learning algorithm. It will learn from its mistake. You are seeing. So they are having some 3 models, and each and everything is doing its work. Not only the machines, we are also learning from we should learn from our mistakes. Okay, this is the Google DeepMind, and finally, so you can browse these things in the net also. AlphaGo is also the self-learning algorithm. The machine beats the human brain, that is in machine masters, and it defeats the human. So these are some of the references. Thank you for your patience. I have taken much more of your time. Thank you for your patience and listening. Any questions you can ask, free to ask.
Thank you, ma'am. Participants, you can just unmute yourself and ask any queries, doubts if you have any to ma'am.
Ma'am, one question is on chat box. Sudalai ma'am asking, can RNN used for food ulcer clustering, ma'am?
Of course, it can be used. Recurrent neural network can be used for any, for even we have used in, actually we have used the fast RNN for the agriculture sector research, but the same can be applied for the medical side also.
Okay.
If you have any queries, suppose offline also, you can mail me. My mail ID is there, suganya@cac.nits.ac.in. So I'll be replying the mail if you have any queries regarding your research. And if you want any collaboration also, I'll be helping you in that record, in this record.
With that note, I think we will come to a end of the session. So it is my pleasure on behalf of the Department of Biomedical Engineering and organizing team of this Sttp to thank Dr. K. Suganya Devi, who has given a very good insight into the pattern recognition and medical imaging concepts, who happens to be the assistant professor grade 1 from the Department of Computer Science and Engineering, NIT Silchar, Assam. Thank you very much, ma'am.
Thank you, sir.
Thank you, ma'am. Dear participants,
Thank you, ma'am.
we can just break
Thank
for
you
lunch
all the
and be back.
coordinators and attendees for your patience.
Thank you.
Dear participants, we can just break for lunch and we can just be back by 2 o'clock for the final session of the day. Thank you, Anandal. Thank you.
Okay, thank you, Sudha ma'am. May I leave?
Yes,
May I
ma'am.
leave?
Thank you, ma'am. Can leave, ma'am, now.
And another thing, could you please share the feedback of those things?
Yes, ma'am. Definitely, ma'am.
Okay. Thank you, ma'am. Thanks a lot. Bye. Have a nice day.